So we remind you to all speakers that the talk will be of 20 minutes. So we recommend 15 plus 5 minutes for questions and answers.
Well, I'm sorry, we have 5 minutes during, I mean, at the end of the talk or at the end of the session?
No, at the end of the talk.
Oh, okay.
Yeah, I mean, we have to be rather precise because unfortunately the connection, the Zoom connection, will be closed at about 7:30, so we cannot really be very late.
Okay.
But, okay, so I mean.
Yes, it goes over the official time at most 15 minutes. Then it shuts down automatically. We can do anything to avoid that. Okay, so I think we can start with the first speaker because Atul didn't share the screen, but okay. So the first speaker, Kent, are you ready? Oh, here you are.
Yes, I am.
So start when you are ready.
Okay. First, I would like to thank the chair for inviting me to this very interesting session. And today I would like to explain how we can use recent NICER and LIGO-VAGO collaborations measurement of neutron stars to measure some of the nuclear matter parameters. And my talk is based on some of the papers that I wrote together with these collaborators. All right. So to get started, I'm sure you know that LIGO-VAGO collaboration has measured tidal deformability through gravitational wave observations, and tidal deformability, to remind you, is given by the ratio between the amount of tidal induced quadrupole moment of a neutron star due to the tidal field strength created by a companion. And I denote here the tidal deformability by lambda. And what actually LIGO-VAGO collaboration measured is the leading tidal parameter in the waveform, and that's given by a combination of two tidal deformabilities, lambda 1 and lambda 2, for two neutron stars inside the binary system, plus it has some dependence on the mass ratio Q. And then this is the actual probability distribution that they reported. And let's see. On the other hand, NICER has successfully measured the mass and especially the radius of a few pulsars. And for example, if you use the first pulsar that they reported, then in the mass radius relation plot that I took from this paper, then you can compare the mass radius estimate from NICER against mass radius estimate from gravitational waves. And we can convert the tidal deformability measurement to a radius mass measurement. So these red and blue are the ones obtained from gravitational wave observations. And then NICER prefers stiffer equilibrium state with larger radii. Gravitational wave prefers softer equilibrium state with smaller radii, but there's an overlap between the two. And my talk today's focus is to use these observations of NICER and LIGO-VAGO collaborations to measure nuclear parameters. And we followed the approach that has been taken extensively by nuclear physicists. And the idea is to take first energy per nucleon, which depends on two parameters, n and delta. N is the total number density. So it's the sum of the neutron number density and proton number density. The second parameter is delta, that is measuring the difference between these two number densities. So this is a measure of asymmetry in this nuclear matter. So first we can take this energy per nucleon and then expand about delta equals 0. In other words, expand about the symmetry nuclear matter. And the leading is the energy corresponding to symmetric nuclear matter. And the next two leading captures the information about asymmetry. Then for each of these coefficients, we can further expand about the saturation density and naught. For example, if we take this second term coefficient and then expand about nuclear saturation density and naught, then we get all these Taylor coefficients. The leading constant piece is the symmetry energy. The next leading is its slope. The next leading is its curvature, and we can just keep going. For the lower order parameters like symmetry, energy, and its slope, we can use terrestrial experiments, nuclear experiments to more or less measure these quantities, but it becomes more and more difficult to measure higher order quantities because those higher order quantities only come into play when the density goes beyond nuclear saturation density. So these are the parameters that are difficult to measure, but here comes neutron star observations. Since central density goes beyond saturation density, some of the neutron star observables have strong correlation with these parameters. So my focus today is to measure this curvature of symmetry energy K through neutron star observations by using certain correlations. And for that, we use 3 different types of equation of state. The Scrum type in green, relativistic mean field in blue, and then phenomenologically varied equation of state in red. This last one, phenomenological one, is that we take the nuclear parameterization that I explained in the previous slide, and then just vary all the parameters included in that expansion. And you can see in this mass radius relation that Scrum type prefers softer equation of state with smaller radii. RMF generates stiffer equation of state with larger radii, and then phenomenologically varied equation of state brackets the two, so it varies from soft equation of state to stiff equation of state. Then what we did was we take one equation of state that has a unique curvature symmetry energy K, and we compute the tidal deformability lambda tilde that LIGO-VAGO measured with gravitational waves event G1170 and 17. Then we can plot a point in this parameter space of K versus lambda tilde. Then repeat this for all the other equation of state, and we get all these dots in this plot. And you can see that there's a nice correlation between these 2 parameters for all 3 types of equation of state. And the blue shaded region is the measurement on lambda tilde made by the LIGO-VAGO collaboration. So what we can do is we can use LIGO-VAGO's measurement on lambda tilde, and we apply that measurement to this correlation, and then we infer the information about this curvature of symmetry energy K. And to do so, we need to first prepare a conditional probability distribution on K parameter for a given lambda tilde. We multiply this by LIGO-VAGO's measurement on lambda tilde. We integrate over lambda tilde to get the probability distribution on the K parameter that we want to measure. So we need basically this first quantity inside the integrand, which we obtain through the scattering plot that I showed you earlier. All these dots correspond to red, blue, or green dots shown in the previous slide. Here, for simplicity, we assumed that the distribution in this 2-dimensional plane is a 2-dimensional Gaussian. And then we constructed this 2-dimensional Gaussian probability distribution out of these data sets. This could be a strong assumption, so we will relax this Gaussian assumption later. But for now, let's assume for simplicity that the distribution is Gaussian. Once we make this assumption, we can construct a simple 2-dimensional Gaussian probability distribution. We multiply this by LIGO-VAGO collaboration's measurement on lambda tilde. Again, we integrate over lambda tilde, and we get the posterior distribution on K. And the result is shown in this curve, green curve with a green shaded region corresponding to a 90% credible region on the measurement of K sim, the symmetry energy curvature. And notice that the distribution is almost Gaussian, is precisely coming from our assumption that the distribution in the K parameter and lambda tilde is a 2-dimensional Gaussian. Next, we repeated a similar analysis for NICER. What NICER measured was radius. So we first looked at the correlation between this curvature symmetry energy against the radius for a fixed mass. As an example, I show here the radius of a neutron star with mass at 1.4 solar mass. And then there is some correlation in this parameter space as well. So we combined this correlation again against the NICER measurement of mass and radius, and then basically we repeated a similar analysis to the gravitational wave case. And let's compare the outcome. So this green curve is what I already showed you earlier using gravitational wave alone. And then if I use instead NICER measurement alone, then the distribution becomes this blue one. there is a shift in the peak location. NICER prefers a larger body of coverage of symmetry energy because NICER prefers different equilibrium state. And we can even combine these two different observations to get the combined probability distribution, which is shown by the red curve. And you can see that the central body of this K parameter is somewhere around -100 MeV. All right. As I said, we have made some assumption, and the main assumption is that we assume that distribution is two-dimensional Gaussian, and we try to relax this assumption, and it seems more plausible to find the conditional probability distribution of K for a given lambda tilde from the actual scattering data rather than assuming that it's a Gaussian distribution. And the reason why we didn't do that in the original analysis is because we didn't have enough number of equilibrium states. Previously, we only had like 30 different equilibrium states. So to relax this Gaussian assumption, we generated more number of equations of state, and we ended up generating 30,000 equilibrium states roughly. All of them support two solar mass neutron star and preserve causality. So we are going to use this new data set and then get directly the distribution on K for given lambda tilde. We try to relax another assumption, which is that in the expansion of nuclear energy per nucleon that I explained earlier, I truncated at the second order, and I was focusing on this curvature of symmetry energy. We could go one order higher, and we tried to look for the effect of this higher coefficient, which we call J, on the bound on KCM. Okay. So this plot shows a comparison between the original data set for the curvature of symmetry energy as a function of lambda tilde in red against the new data set in blue, where for the new one, we added this higher order J parameter. And you can clearly see that addition of this higher order parameter makes the scattering much wider. But one thing to note is that realistic equilibrium states like SCARM and RMF followed the original relation in red, as I showed you in my previous slide. So this sounds like if we use realistic equilibrium state, then there are some explicit correlations between different nuclear parameters like K and J and L and so on that actually makes the correlation between K and neutron subsamples much tighter. And then the outcome is very similar to the case without the higher order parameter like J. And indeed, there is a recent paper by Malik et al. Showing that indeed, within at least the SCARM framework, there are such explicit correlations between nuclear parameters. And once you impose that, then the correlation between K parameter or other nuclear parameters and neutron star levels becomes much tighter. In any event, we use now this new data set and then try to find the conditional probability distribution of K for a given lambda tilde directly from this new data set. And to do so, we split this blue data set into two pieces. One is where we just focus on the case where there is no higher order parameter J. So we just set J equals 0 and then use a subset of this blue data set where J is being set to 0, which is more consistent with the realistic equilibrium state. The second analysis is we take a more conservative approach. We don't assume any correlation among nuclear parameters, and then we use the full data set shown in blue. And for both of these cases, we use the actual data to construct this P conditional distribution directly. All right, so this red curve on the left panel shows the new distribution on the K parameter, assuming that the high order contribution is 0 without making an assumption of two-dimensional Gaussian distribution. Again, the distribution is obtained directly from the data set. And comparing this against the red curve on the right plot that I've showed you earlier, assuming a two-dimensional Gaussian distribution, then you can see that the new distribution is no longer Gaussian and it has some skewness. But for example, the peak value stays the same. It's still -100 MeV. Then the more conservative analysis of case is where we varied this higher order parameter J, and then because the scattering becomes wider, the bounds on K sim becomes much weaker, and also the peak shifts to a smaller value of K, which is consistent with some of the previous analyses where inclusion of J tends to make this K value smaller. These two different cases give us two different distributions. The realistic equation state seems to be more consistent with the red one, but if we take more conservative standpoint, then the distribution becomes this magenta one. Okay, and before ending my talk, I'd like to comment on some of other related analyses. Here I show some selected examples. For example, this paper looked at the radius measurement of quiescent low mass XR binaries and found measurement on K value. The next paper looked at the LIGO-VAGO measurement and also NICER's 2 pulsar measurement, including the 2 solar mass pulsar one, and then did the analysis, and they found, for example, the allowed region in this 3-dimensional parameter space of nuclear parameters, including K-sim. The third one is also an interesting paper where they constructed a hybrid equilibrium state where in the low density regime, they use this nuclear parameterization that I explained in my talk. For the high density regime, they stitched this nuclear parameterization against a piecewise polytrope equilibrium state. Then they studied or they used the gravitational wave measurement and also X-ray measurement to get a bound on K-sim. And you can find some recent reviews here. Okay, so just to conclude, we looked at some scattering relation in nuclear parameters and neutron star observables, and then we applied these correlations to gravitational wave observations of tidal measurement and X-ray observations through NICER of radius measurement. And we found these two different distributions. The realistic recurrence seems to be more consistent with the red one. And then the inclusion of higher order nuclear parameter J made the distribution wider and more conservative. But yeah, again, it looks like realistic recursion state seems to follow closely this red one. Okay, that's it for my part. Thank you very much for your attention.
Thank you. Thank you very much. Are there any questions? Please ask, raise your hand or just ask the question.
May I ask a question?
Yeah.
So maybe I missed the point. What is the value of L that you have used? So the derivative of the simultaneous energy, because this is quite uncertain. So
yeah,
I wonder whether
L,
the choice that you have on L could spoil a little bit your result.
So we varied over L, assuming some uniform distribution, and the range is taken from one of the nuclear parameters. And then, so we didn't fix any L, rather we take some range and then varied over L and also other parameters. And that's why we are seeing this variation, this kind of scattering. So we not only vary K, but we also vary other nuclear parameters.
Yeah, may I also ask a question? Maybe I also missed something. In your analysis, are you considering only equations of state which are based on nucleonic degrees of freedom, or you also consider, I don't know, equations of state in which you can produce hyperons, so you can have phase transition or whatever?
For our analysis, we focus on nucleonic equilibrium state. So yeah, it might be interesting to see how the results change as we include those hyperons and so on. But I assume those only entered high density part, where we are looking at sort of region more or less close to saturation density. So probably they won't have much effect. But yeah, I agree. It would be interesting to see how the results change if we add hyperons or quark matter degrees of freedom.
Yeah, because of course the expansion that you're making is an expansion around rho zero, but after the observables are observables that are testing globally, the structure of the object.
Yeah.
So it can be delicate in a sense.
Yes. Yes. Yes.
May I ask a question to Kent?
Yes, sure.
What happens if you don't use LIGO results? And for example, if you include PREX to the PRX 2 bound.
Oh, I see.
Well,
Do they? Let's see. So I'm not familiar with PREX measurement, but my impression is that it's difficult to measure this K value. I think they are more sensitive. Their measurement is more sensitive to these lower parameters like J naught and L naught. And I don't recall any paper seeing bounds on Ksin using PREX, but I might be misremembering. But that's my impression.
Okay, so thanks again for this very interesting talk.
Thank you.
And we can switch to the second speaker, who is Danny Page. Danny, please.
Hello. Okay. So I share my screen, I guess.
Yeah.
Okay. Here we are. Okay. Let me try to get rid of the Zoom. No way. Okay. So thank you again for the invitation to talk at this very interesting meeting. So I decided to talk about something that came out in the last 2 years and which could be very likely a first sign of the neutron star 1987A in the supernova 1987A, which is something we've been waiting for like more than 30 years. So in my talk, I'm going to give you a brief description of the supernova itself, its remnant, and then the somewhat evidence for a compact source, or more likely to say a sign. It's like a smoking gun. And I will compare a bit with a very similar supernova remnant, which is the Cassiopeia A. And then I show you the argument to show that this sign form is actually evident for the presence of a neutron star. And I will tell you finally, if I have time, what we can learn from this. So let's look at the supernova 1987A. So it occurred on the 23rd of February, 87A. Well, discovered by Ian Shelton in Las Campanas Observatory in Chile. And it was the first supernova visible by eye since Kepler. Even so, there's possibility that Flamsteed in 1680 did see the supernova from Cassiopeia A, but not everybody agrees that what Flamsteed see was really the supernova. So here at 1987A, so it's occurred in the Large Magellanic Cloud, 55 kiloparsecs away. Here is the explosion of the star the day after the explosion. And luckily, the star couldn't be found in previous photo of this region, and the progenitor has been identified. It was a blue supergiant, was about 15 solar mass at the time of explosion, and a stellar evolution model indicated that it was born with about 20 solar mass, and it lost 15 solar mass during its evolution, which is very common for very massive stars. They have very strong winds. And as you all know, neutrinos was observed 8 in the IMB detectors in the US and 12 in Kamiokande. So this was, the neutrinos were evident that the neutron star was formed there. The big question is that, well, was it after? Some people say, well, since it was not showing up, that it collapsed into a black hole. Now, everything indicated from the neutrinos and the model for the evolution of the progenitor that the star that was produced, the neutron star, was about, let's say, 1.2 to 1.8 solar mass. So now, since 2010, we know that we have radio pulsar that more than 2 solar mass. So the idea that this neutron star may have collapsed into a black hole has basically gone with the discovery of the 2 solar mass pulsars. But before this, for many years, people were speculating that maybe the neutron star collapsed into a black hole just after being formed. So let me now look at the remnant. So there's a very nice image of it. These 2 dots are stars in our galaxy, but the remnant is there. Okay, and these rings are material ejected by the progenitor. Remember, it lost 5 solar mass of material during its life, and these were illuminated by the UV radiation from the explosion. So if this is a 3D rendering, an artist image of what the remnant looks like, and the center part is bright, is energized at present time by radioactive of titanium-44. There's nothing special about titanium-44. It just happened to be a radioactive isotope that is there, and it has a lifetime of 60 years. So it is at present time the main source of energy. And here is basically the size of the remnant, the distance 165,000 light years. And what we see in this image, this loop, here the equatorial loop, is material that was ejected by the progenitor, but that was hit by the explosion, by the shock wave of the explosion. So it's basically is material from the envelope, which means it is hydrogen and helium mostly. And in the center, we have the debris, which are heavy element that was synthesized by the star during its life. And this cooled down very rapidly during the expansion, and a few months after the explosion, it's starting solidifying and it starts making dust. So basically there is like half a solar mass of dust in the center of the remnant, and this is very obscuring the center. So it's impossible, at least at present time, to really see what's deeply inside the star, inside the remnant. Now, the evidence or the first sign for the compact source was published at the end of 2019. It's actually an observation from 2015 from the ALMA observatory. So this is made of 66 antenna in the northern Chile. Here it is on Google Earth or Google Map, and this is Bolivia, and it's just close to the border. So it's about 5,000 meters high. So it allows them to go a little bit deeper in the infrared compared to if they were at sea level. And in 2000, it was inaugurated in 2011. In 2015, they used the widest configuration by moving the antenna. They had like a separation of 16 kilometers, so they got a very high angular resolution. And these are what they did. Well, that's an image that not at the highest angular resolution, but it shows the equatorial ring from ALMA and the same from the Hubble. So you see that the H alpha, which hydrogen emission, there is almost nothing special in the center. When you go to 315 gigahertz, so it's about 1 millimeter wavelength, you see a bright spot in the center. Now in 2015, they could go to higher frequency. You see heat at 600 hertz, so it's half a millimeter, so it gives you better resolution. And they show what they see as contour, which are 3 sigma, and even one little blob that is 5 sigma above background. This cross is the center of the explosion, so it's a little bit off center. And they had a hard time to explain the brightness of this blob, and they postulated that it's probably a sign from the central compact object. And you need about 40 to 90 solar luminosity to explain this. So basically that's it. No? It's a blob of dust. They call it hot or warm. It's actually at 33 Kelvin, while the ambient dust is at about 20 Kelvin. No? And to heat it from 20 Kelvin to 30 Kelvin, you need about, let's say, 40 to 50 solar luminosity, an extra source. And we examined this in detail, and it turned out that the radioactivity of the titanium, which heats dust, cannot be responsible for this extra 40 solar luminosity. The blob is not deep enough to, even if it were a concentration of titanium 44 there, the blob is basically optically thin to the gamma rays from the titanium. So it cannot be heated by the titanium itself by some anomaly in the density. There is an extra source there. And then the question, of course, what is this extra source? So let me look at the sister of 1987A, which is Cassiopeia A. And that's the remnant observed in X-ray by Chandra. And the first light of Chandra, August 1999, they found the neutron star. So right in the center, not exactly in the center, but almost in the center of the explosion, there's a neutron star. It is not a pulsar. It doesn't have a synchrotron nebula. It's just a blob of hot matter that emit X-rays at the time with a temperature about 2 million Kelvin and nothing else. Interestingly, people have been able to reconstitute the 3D geometry of the remnant. It's the most studied one because it's the youngest one and relatively nearby, and it's strongly anisotropic. You see here what can be reconstructed. They have jets of matter coming out, and even the matter, the different elements produced in this onion shell structure by the progenitor are being inverted. You find the iron is outside the argon and silicon. So that represents really the wild explosion. And there is evidence that something similar happened in 1987A. This is an observation from 2016 in the optical when this is a silicon and iron from the Doppler shift. You can reconstruct the 3D geometry. And this is 1 year later, a paper by Thomas Chanka, one of our collaborators. By doing 3D anisotropic explosion, they found a model that looked pretty similar to that one. And they get similar distribution. And from the velocity and the mass of the matter being ejected, by momentum conservation, they could predict where the neutron star should be moving. And remember, I showed you in the image that the neutron star is not in the center. And so they predict that the neutron star is moving at velocity between 200 and 700 kilometers per second. And remember, this is the center of the explosion. This is where it is a blob. And this is exactly the direction in which a simulation predicts the neutron star should be. So in some sense, I like to call this like the duck story, no? That it walks like a duck, it has feathers and it makes quacks. So what is it? It is a duck. So this one walks in the right direction. Now, where does energy come from? It could be a pulsar. So let's look at the pulsar catalog. So these are almost 2,800 pulsar from the ATNF catalog. You know the trick from this, from P and P dot, we can get the magnetic field of this object and the age. But the magnetic field has some amount of theory, and the age is just an estimate of it, P over 2 P dot. There's something more interesting we can do is the spin down energy of it. Can calculate the rotational energy. Omega is measured. The moment of inertia, we know quite it well. There is enough constraint on the mass and the radius and the size of the neutron star, that moment of inertia between 1 and 2 10 to the 45. And the spin down power, the derivative of this is E I omega omega dot. Omega omega dot are measured for this pulsar. So we have a factor of 2 uncertainty from I. So here are the results. So line of constant spin down from the pulsar. This is the energy we need to power the dust, the blob. So it's reasonable amount of energy. And all the red dots are young neutron stars that are inside a supernova remnant. However, it's important to notice that the range from the young object, you have some CCO that are at 10 to the 31 ergs per second, the crab 10 to the 39, and here we need 10 to the 35 between a factor of 2 or 3. So yes, it could be a pulsar, but you need fine tuning, and it's okay. You need a lot of fine tuning for it to work. However, we have another category of object. I mean, this is like Cassiopeia A. I showed you that this is just a neutron star. It's not a pulsar. It doesn't emit, it only emits thermal X-rays, no? There are other objects like this, like Puppis A, nearby the Vela, the supernova remnant. This is a Vela pulsar. It is a pulsar. Puppis A contains a central compact object, just a bright young neutron star emitting thermal X-ray. At present time, there is about a dozen of these central compact objects. In 3 of them, P and P dot have been measured. So they call pulsars, but it's not pulse like a normal pulsar. It's just a slight modulation. Here's the pulse fraction of it. So they find this one has very high pulse fraction, 64%, but this one 11 or 9%. So they're barely detectable. And so these are measured. The other one, I mean, there's no measure of P and P dot. And if you take the pulsar younger than 10,000 years from the pulsar catalog, you have regular pulsars, you have high field pulsar. So in total, from the young object, less than 10,000 years, you have 11 CCOs, 21 radio pulsars, and 11 magnetars. So the non-magnetized or weakly magnetized neutron stars, they're about 25% of the young population. Turn out actually that by looking at the properties of the explosion with Sasha Muslimov and then with Ulrich Gepper and Thomas Sanyas, we even predicted in the 1990 that the neutron star 1987, it should not be a pulsar, it should rather be a CCO. Actually, we did this even before the CCO were given a name. So, okay, so if not a radio pulsar, what is it? What would power it? So a proposal is that it's actually just a cooling neutron star. It's just a CCO. And let's look at here a family of cooling curve from the minimal cooling. And here is the luminosity that is needed to power the hot blob. It's right on the spot for a star that's 30 years old. That's exactly what cooling theory predicts it should be. There is some range. Here I will describe it depending on what amount of, what is the surface of the star actually made of. If you have any element to the surface, like the neutron star in Shapiro's and Tucholsky book, which tell you that low density is made of iron. So if you have iron or other heavy element, it would be relatively cold. If you have light element that may have been accreted just after the explosion, then it could look much hotter. So actually, it's right on the spot that the energy needed for the blood is exactly what you expect. So what controls the temperature is interesting, that the cooling at that time is determined by neutrinos. This is the range of temperature you have in the outer crust, in the crust of the neutron star. And initially, when it's hot, it's cooling by plasmon emission. Then when the temperature drops below the plasma temperature, plasmon emission stops and the star stops cooling, which is actually what you see here. Here, temperature profile of a heavy star that where the core cools rapidly by neutron emission, less heavy star when the core does not cool rapidly. If you look at the outer part, the temperature profile, this is the temperature versus density. The temperature profile of the crust are basically identical in both models at early time. And you see the temperature cool, the outer part of the star cool very rapidly, and then it gets stuck here for like 10, 20, maybe 30 years. That's because the temperature drops below the plasma temperature. There's no more plasmon neutrino turn off. And the next neutrino process, the electron ion beam shallow, is very inefficient. So that's why the star stopped there. And that's why we have this early plateau here. And so it's just basically the plasma temperature in the outer crust that determines that the cooling will stop. It gets stuck from some time until some other process take over. And it gives us exactly the right temperature. So the conclusion is that it's very likely a CCO, another one. So let me take 2 more minutes and see what we can learn from this. Here, I call this a Christmas tree figure. So we look at, we plot the surface luminosity and versus age. This is the power needed to power the blob of dust. So in each panel, we change the core. And within each panel, we change the crust physics. So for example, we use a stiff equation of state or a soft equation of state, or within the soft equation of state, we change the mass. We can also change the superfluidity and superconductivity in the core, known at all, proton superconductivity, neutron superfluidity. Basically, you look at all these figures at early time when we see 1987, they basically all look the same. No? So thanks to the constraint and the equation of state that we need a mass of more than 2 solar mass, and the radius is relatively constrained by NICER, by the observation low mass X-ray binaries, by gravitational wave. You cannot do crazy things with the equation of state. So it turns out that the early cooling is not so much dependent on the equation of state. It will depend on what's happening in the core. So here I change the core physics. This is a light element at the surface. So it has accreted junk after the explosion. Depending on how deep the light element go, light elements have low Z, so they have a higher thermal conductivity. So even if the interior of the star is exactly the same in all these models, the surface look different because having light element, the heat can come out more easily. So depending on the amount of light element or the thickness of this layer, you can increase the temperature. And you see the lower part, or even this is the range of luminosity you need if you accept that the blob is preheated by titanium-44, and then up to temperature of about 20 Kelvin, and then it is heated to 30 Kelvin from the compact object. So that would be the minimal range of luminosity we need. So if you actuate up to about 10 to the 9 gram per cubic centimeter, you get a perfect explanation of this. So basically we have it. So I have a conclusion. We could say that it's, of course, it's just a hot blob of dust close to the center, but it is located a bit off center, and it is exactly in the direction where the model of the explosion predict it should be. The power that's needed to hit the blob could be actually from a pulsar, but you need fine tuning within 8 orders of magnitude. However, about 25% of young neutron stars are not pulsars, they're CCOs. So it's quite probable that 1987A with 25% probability could be a CCO. And actually, we had predicted from the property of the explosion that the magnetic field should have been destroyed by the post-explosion accretion. And it turned out that thermal radiation from the 33 years old neutron star give you exactly what you need. And I will stop here.
Thanks a lot, Danny, for this extremely interesting talk and topic that has been puzzling everybody for tens of years. And one or two rapid questions, maybe. Maybe I will ask myself a first question. Do you think that the possibility that this central object is a quark star is definitively ruled out by the data?
Yeah, yeah, because if it were a quark star, I mean, you mean a strange star made of strange matter.
Yeah.
These are very thin crust.
Yeah.
So if you look at this cooling, I mean, something like this, no?
Yeah.
Here it can last about, well, the better figure would be that one, no? You see here when it goes cooling, the core is cold, and then you have like a cold wave propagating to the surface. Here you see more dramatically, no?
Yeah.
So it takes some time. So the surface stays warm for a given amount of time because the crust is thick.
Yeah.
So if you have a strange star with a very thin crust, the temperature would drop after 1 or 2 years. There's no way it could last 30 years. But unless the neutron emission in the core is very low, so the core is not cooling. So instead of having something that drop and then go the direction, maybe it would just stay hot for a long time because it's not emitting neutrinos. No? So that could salvage the situation of a quark star if you want.
Thanks a lot.
So it needs not to emit neutrinos. No? It has to be completely superconducting, everything.
Yeah.
Then it will work. Yes.
Yeah.
May I have a short question?
Yes.
Yeah.
Quick. If you forget about that, if you assume that that power, that heating comes from the pulsar activity, the traditional pulsar activity, and you estimate the magnetic field of the neutron star, what would be the value? And is this in contradiction with the hypercritical accretion at the beginning? I mean, it would come too high.
Okay, this is the range you need. Okay, so depending on P, it could be 10 to the 8 Gauss, or it could be 10 to the 12 Gauss, no? It has to be in this range. So yes, if it were a millisecond at 10 to the 8 Gauss, that would work. Actually, there were claimed by Middle Dish that they were seeing optical pulsation. That was in 1990. I know much people don't believe it, but still, I heard him talk several times. He say, we do see 3 millisecond pulsation. So 3 milliseconds is here. So it could be a millisecond pulsar with 10 to the 8 Gauss, and that would work, yeah.
Okay, thank you.
You need fine-tuning, but it works, yeah.
Thanks, Danny. Very nice talk.
You still have the thermal emission from the surface. This is unavoidable, no? You cannot hide the neutron star, no?
Yes.
So it would come on top of this. If someday we see pulsation, then that would be a confirmation. We would get P dot, no? If you see the pulsation. I mean, P, at least we would get P, the period. If it's 1 second, then it's not going to work.
You know where Middle Ditch is these days? Is still active? Middleditch?
I don't know. I heard him give a talk in Los Alamos many years ago. He was discussing this, and it lasted many years, and finally it was published. And he was working with several groups of pretty good people, and they're saying they were seeing this 3 millisecond pulsation. So I don't know. I don't know. I don't know if anybody has disproved. You cannot disprove that he didn't see it. No? Let's say maybe nobody confirmed it. But I think they had 3 observations by different groups.
Yes.
So
And
that
today is possible. Well,
So-
this is very interesting. I
Yeah.
still remember the discussion many years ago on this, and how animated was John Middleditch discussion.
Yeah. He's a funny guy, no?
Correctly so. Okay.
Good.
Good.
So thank you very much, Danny, for this
Yeah.
beautiful talk. And as we move forward to Giuseppe Pagliara.
Okay.
Giuseppe, are you ready?
Giuseppe,
Cosa-
where?
I can show my face also. Let me see if it works.
Okay, start when you are, as soon as you are ready. Okay, good.
Just a moment. Okay, do you see?
Fine. Yep, you see the
Yeah.
screen.
Okay, so I thank the organizer for giving me this opportunity. I will talk about a recent work we have published on PRL about the interpretation of GW 1908-14. Well, and our interpretation is in terms of quark star. So I will explain how, why, and how. Okay, so the thing is the following, that this was a system with a black hole of about 23 solar masses and a low mass companion with a mass of the order of 2.6 solar masses. Now, this number is interesting because it falls in what is called the low mass gap of black holes. So it is not clear whether this is the lightest black hole or if it is instead the heaviest neutron star. Now, I will not discuss here the black hole interpretations. There are many of them. Tripole system, so the system was actually a tripole system. It could be a primordial black hole. It could be due to a supernova with a lot of material left after the explosion that then made the collapse of the neutron star into a black hole, extended gravity, and so on and so forth. So I will not discuss the black hole interpretation. I will discuss instead the neutron star interpretation. Just to set up the language, actually, is very common. When talking about neutron stars, of course, what is important is the equational state. And generally speaking, one can divide the equational state into categories, let's say stiff and soft. Stiff means large masses, large radii. Soft means small maximum masses and small radii. And another point is that for a stiff equational state, a fixed gravitational mass, the central density is smaller. So if I take a 2 solar mass object, for instance, and the equational state is stiff, then the central density is, let's say in this example, specifically is 4 times saturation density. If I take a softer equational state, the central density increases and could be as large as 10 times saturation density. Now, let me discuss neutron star interpretations. Basically, there are 2 possible interpretations, to my knowledge. The first one is that actually the maximum mass of the stars is of the order 2.2, and this number is obtained from several measurements and direct measurements and several analysis, including also a very recent and interesting Bayesian analysis on GW 170817, in which, by including also the constraints coming from the kilonova, it has been inferred that the maximum mass is of the order of 2.1 solar masses, and the radius of the 1.4 solar mass configuration is small, actually is of the order of 11 kilometers. That means that the equational state is not too stiff, let's say, okay? Because such a small radius is actually pointing to quite, well, it's pointing towards soft equations of state. So then the idea, if the maximum mass is 2.2, is that to reach 2.6 solar masses, you need rotation. And this scenario is possible, although one has to explain why such an old object could still keeping a very high frequency of rotation. Because to get, of course, a significant effect on the mass, you need a rotation, a frequency which is close to the Keplerian limit. The other interpretation is that actually the equation of state is stiff. Actually, it's very stiff. You can reach, even without rotation, 2.6 solar masses, as in this example. Look at the red line, which is called Big Apple in this paper. You can reach, by exploiting, if you want, the uncertainties on nuclear matter, you can reach 2.6. But on the other hand, when having such a stiff equation of state, it is difficult to reconcile with low energy heavy ions data. So this red line here corresponds to the equation of state, which is out of this experimental constraint. So there are some problems in these two interpretations. And let me discuss a little bit why this object, if it is a neutron star, is also interesting from the point of view of the composition. This is a general result that has been obtained by Latimer and al., in which you can see which is the constraint on the central density depending on the mass, or well, depending on the maximum mass. So if you sit at about 2.6, you realize that the central density using all the constraints that we have must be larger than about 5 times saturation density. This is a large number, and maybe it's not conceivable to assume that at such large densities actually just neutrons and protons appear. But maybe it's important to consider at that point also hyperons, delta resonance, and so on and so forth. Now, when including those particles, generally speaking, you have a softening channel. So in principle, that would reduce the maximum mass. And therefore, in order to assume that such an object of 2.6 solar mass exists, one has to explain why hyperons are not softening so much the equation of state. To my knowledge, there are no calculations with hyperonic stars, for instance, able to reach this number, so this 2.6. Because, as I said before, hyperons usually provide a softening challenge. Let me just show a few mass radii measurements. Of course, we have evidence of object with a mass of the order of, well, above 2 solar masses, of the order of 2.1 solar masses. But there are also indications of small radii, not only from the GW 170817, but also from quiescent low mass X-ray binaries, and other analysis pointing to radii for 1.4 less than 12 kilometers. Actually, in this example, for instance, the central value is close to 11 kilometers. On the other hand, there are also cases in which radii are large. In this case, 13 kilometers, and in this case also above, let's say, 12 kilometers. So those data, putting everything together, it seems like the equation of state sometimes is stiff and sometimes is soft. And actually, as you will see, our interpretation is that it could be both somehow. Let me also mention the nicer results. Also in this case, actually, when looking at the numbers, although the error bars are large, but for 2 solar masses, the central value is close to 14 kilometers. Whereas for a 1.44, the radius, the central value is close to 13 kilometers, and that is pointing again towards stiff equation of state. Now, as I said before, by collecting all the data and all the information, it seems like that sometimes it's stiff and sometimes it's soft, and that's why we have provided an interpretation a few years ago in terms of 2 families of stars. So what we are saying is that there could exist 2 families of stars. One is made of hadronic stars, in which also hyperons and deltas could form. And we don't care about how much those particles actually soften the equation of state, because on the other hand, we are assuming under the hypothesis of absolute stability of strange matter, we are assuming that the second family of stars exists, which is the family of quark stars. So as you see in this example, while a hadronic star will fulfill low radii suggestions, the existence of massive stars will be actually more suitable for, well, is explained in terms of quark stars. Actually, one can reach easily numbers above, quite above 2 solar masses with quark stars, okay? And the two families would coexist in our scenario. Now, how to reach 2.6 solar masses with quark stars? When a possibility is that when one includes a color superconductivity, in this case, we have just included as an example the CFL phase, and we have basically explored the parameter space. In order to have 2.5, 2.6, we need, well, the conclusion is that we need a quite sizable value of the superconducting gap of the order, let's say, of values close to 100 MeV. So it's an important superconducting gap. So it's easy to reach 2.6, but one has to assume maybe, for instance, superconducting gap in the central part of the star. And when putting everything together, as you see in this plot, we can reach 2.6 with quark stars, and we can also have stars with small radii. Indeed, when sitting at 1.4, we could have objects with radii of the order of 13 kilometers, which are interpreted in our scenarios as quark stars, but we can have also radii of the order of 11 kilometers, which are interpreted in our case as being hadronic stars. And what happens at 2 solar masses? At 2 solar masses, our interpretation is that definitely such an object is a quark star, and the radius must be close to 14 kilometers, which is in agreement with the recent NICER results. I think I lost my time. I guess I have maybe 10 minutes left. So let me explain how can two families coexist. And the thing is that strange quark matter is absolutely stable. When strange quark matter is absolutely stable, of course, this is a minimum of the energy. But in order to form this kind of matter, you need a lot of strangeness. And the way you can fulfill this requirement is to have enough hyperons in the core of a hadronic star. Once you have enough hyperons, you can make nucleation, or you can describe the process as due to nucleation, for instance, and jump from a hadronic star configuration into a quark star configuration at fixed baryonic mass. So if you have two stars here with the same baryonic mass, you see that the gravitational mass of the quark star configuration is smaller with respect to the gravitational mass of the hadronic star configuration, with a depth mass gap, well, energy gap of the order of 0.1 solar masses, which of course is energy released. And there are a number of papers we have published in the last years on the possible signatures of such a conversion process. Let me explain this point. This is a new thing. And the thing is that when you have a conversion of a hadronic star, which is compact, into a stars with a larger radius, this is definitely counterintuitive. How could be such a process exothermic, since it produces a star with a larger radius? The thing is that the intuition, this is counterintuitive because we are not, if one does not consider the possibility of having quark stars, which are stars without lacking a crust. When you do the calculation, you realize that the binding energy of a neutron star can be decomposed into two pieces. One is the nuclear binding energy, and the other one is the gravitational binding energy. Now, what happens in the calculations that we have shown here is that the nuclear binding energy of a neutron star is anti-binding, so is always negative, like this blue dot dashed line, whereas the same quantity for quark star is actually positive, so it's binding. And this is due to the fact that neutron matter is not bounded, whereas a strange quark matter is actually bounded. And so the binding, the nuclear binding that you obtain due to the conversion is actually so strong that it can compensate the decrease in the gravitational binding that is obtained once you have a larger configuration. Okay, so there are not, let's say, strong reason for which a star can convert into a star with a smaller or a larger radius. Here in this plot, we have an example. Well, the point is, the main point is this crossing C between the baryonic mass of the two branches of star. If you take a configuration with a baryonic mass larger than C, you can have a conversion of a hadronic star into a larger star. Whereas if you take a baryonic mass below this C, with this point C, you can have the more intuitive conversion of a hadronic star into a quark star with a smaller radius. But both processes are possible because they are both exothermic, okay? Now, testing the two family scenario, of course, one of the most interesting prediction is that the merger of binaries could be formed by different kind of families. So we can have hadronic star, quark star, and quark star mergers. So the phenomenology is very rich or very complicated. And this is a diagram in which you have the chirp mass of the system and here the mass asymmetry. And depending on those two numbers, you can have all the combination. You can just have hadronic star merger, quark star merger, and so on and so forth. So the phenomenology is very rich and very complicated. We have performed in the past numerical simulation of merger of two hadronic stars. And since our hadronic stars are very small, because the equational state we are considering is soft, what we found is that the threshold mass for the from collapse is of the order of 2.5 solar masses. Now, this is an interesting point because in the standard one family scenario, since for the GW 170817, we have not observed a prompt collapse for 2.73 solar masses, what we expect in one family is that if we have systems with a mass smaller than this number, we do not expect any prompt collapse in the one family scenario. Whereas in the two family scenario, it could be that also with numbers below this 2.73, we could have a prompt collapse to a black hole if the system was made of two hadronic stars. Whereas the GW 170817 in our case is interpreted as a mixed system of a hadronic star and quark star, which did not produce a prompt collapse, but actually produced a remnant and all the nice things that we know. There are other ways to test the scenario. One is the relation between average tidal deformability and radii. Again, at variance with the one family scenario, we could have configuration with a radius which is smaller than about 11 kilometers, and are those numbers here. If the tidal deformability is constrained to be larger than 14, which was the result of numerical simulation in order to obtain a significant amount of matter ejected in the kilonova. So we could have, in our case, let's say, tidal deformability is larger than 400, and at the same time, we could have configuration with radii smaller than about 11 kilometers, what is instead impossible in the one family scenario. So in the one family scenario, the constraints on the tidal deformability are strictly connected with constraints to the on the radii. Speed of sound. Now, this is an interesting point also because when taking this paper is these results are based on piecewise polytropes, so are quite general. They are not particular assumption, but for the existence of just one family of star. And I would like to point out these two things. First of all, when assuming that the conformal limit is fulfilled, so the speed of sound is less than 1/3, the maximum mass can barely reach 2 solar masses, and the radius of the 1.4 configuration is larger than 13 kilometers, which is in this corner here in the plot, in the low right corner of this figure. If the maximum mass is 2.6, as the binary we are talking about is suggesting in a neutron star interpretation, actually not only the conformal limit is violated, but even the causal limit is violated if the radius of the 1.4 configuration is less than 11.8 kilometers. Yes. Yes.
Sorry, in 2 minutes, this time will be over,
okay.
including questions. Including questions.
Including questions. Okay, so again, then I go to the conclusion directly, maybe. Okay. So just to say that 2.6 and 11.8 kilometers is at odds with the results of GW 17017. Okay, so there is a tension. Okay, so to go to the conclusion, we have this scenario of two families of stars. There are many implications of this, and we can interpret the GW 190814 as a quark star. And I conclude just to maybe keep a question or two questions.
Thank you. Is any questions from the audience? In the chat, I don't see any question. There are no questions. Maybe I can make a question. I'm not sure if you can compare, when you compare with the range of masses obtained from GW 170817, because in your model you have different combinations, as you mentioned. So the templates used to extract the numbers for GW 170817, they don't have such a physics that you have in your model. So I don't think that you can compare one-to-one your numbers in the when you are comparing your 2.5 with the 2.73 masses and the masses of also the individual masses for that system. I think, okay, this is a comment.
Well, if you're discussing about the prompt collapse, our result is a numerical simulation result, in the sense that due to the possibility of having a soft equation of state, and so two hadronic stars, the threshold mass is below 2.73.
No, your result, yes, that result is okay. Mm-hmm. What I mean is that you cannot compare that 2.5 solar masses with the 2.73 obtained from the LIGO analysis, because they don't consider those systems you consider.
This is a prediction. So if in the future we will detect, we will have a system with 2.5 showing a prompt collapse, there's no explanation but within this scenario. In one family, you expect not to have prompt collapses for numbers below 2.73, whereas in our case, this is a prediction. We could have prompt collapses.
Yeah, that's fine. Okay. That's fine. That's fine. Thank you.
Okay.
Okay, it seems there are no more questions. Thank you, Giuseppe.
Thanks a lot.
So, bye. Thank you. So we can move forward. Yes. Next talk is Atul. Are you ready, Atul?
Yes, I am. Can you hear me?
You are. Yes.
Okay.
Go ahead.
And I will share my screen. And please let me know if you can see my screen all right.
Yes. The
slides? Okay. So good morning, afternoon, or evening, everyone, depending on where you're located. My name is Atul Kedia. Firstly, before going into my talk, I wanted to thank the organizers and the session chairs for organizing such a wonderful meeting. It's a very exciting meeting with all the great results we're discussing all throughout. Now, going to my talk today, I'm going to be talking about binary neutron star mergers of quark matter-based equations of state. This work is done in collaboration with my collaborators listed here, my advisor, Professor Grant Matthews, Dr. Heel Kim, and Dr. In-Seng Su. So let's get started. Now, Now, before going into binary neutron star mergers and equations of state, I just want to touch base on neutron stars, which I know everyone knows here, but just in case. So neutron stars are really compact objects. They're basically the compact remnants of core collapse supernova explosions for slightly lower mass stars. Their masses are typically in the range of 1.5 to 2 times the mass of the sun, like Giuseppe mentioned in the previous talks. previous talk, and their sizes are also in the range of 10 kilometers, 10 to 12 or 13 kilometers. So you can think of a size of a small town, and that's about the size of a neutron star in terms of the radius or diameter. So all this matter compressed in that small volume implies that there's going to be a lot of gravitational pressure pulling the matter to collapse into a black hole. But due to the neutron degeneracy pressure and further in more higher densities, the repulsive strong nuclear force counterbalances that gravitational pressure. So it's really interesting over here that that all this the micro nuclear physics it gets amplified in the form of its equation of state. We'll get into that later, but it gets amplified and decides what the size of that neutron star is going to be, or the radius of that neutron star is going to be, like Giuseppe also mentioned in the previous talk. So it really, neutron stars really are femtoscopes. I want to say that they probe the physics of femtoscales in the sizes of tens of kilometers or 10 to the 4 meters. So really fascinating objects. Now going into binary neutron star mergers, they're fairly simple in terms of just the term that they're just a merger of two neutron stars. I'm going to play a movie that I made of a merger. So this is two neutron stars just revolving around each other, 1.5 solar mass approximately each, starting at 45 kilometers separation. And you see there's matter flowing out, the tidal and dynamical ejecta flowing out during the merger. Eventually there's electromagnetic and gravitational wave radiation that's emitted, which we observe over here at LIGO or the other electromagnetic counterpart observatories. So so now, why do we want to study binary neutron star mergers? Is because of many different reasons. Firstly, they are the probes to the nuclear equation of state. The nuclear equation of state at the very core, at the highest densities, is sort of uncertain at the moment, whether it's stiff or soft, like said in the previous talk again. So binary neutron star mergers pose to be a very good host where we could study the equation of state. Further, there's questions relating to neutron binary BNSMs that whether the inspiral at large separations is well approximated by post-Newtonian calculations or not, and whether they are the source for short gamma ray bursts, or what's the compact remnant of the merger, and whether it's a hypermassive black hole or neutron star, whether it's a hypermassive neutron star or a black hole, or whether the neutron star goes into collapses to a black hole promptly or later on after some time. All these things, and then further, of course, binary neutron star mergers are also supposed to be, or the ejecta is supposed to be the host for R process nucleosynthesis, a very strong contender for R process nucleosynthesis. So all these are very interesting reasons why we want to study. One should study binary neutron star mergers. In our research, we study just the first of these, which is finding the nuclear equation of state at the core at the highest densities. So now going into how we do that is basically by numerical relativity, which is done by firstly performing space-time evolution by doing a 3+1 split under the BSSN formalism. Further, matter evolution is described by the constrained relativistic hydrodynamic equations and the nuclear equation of state. And all this can be done, the space-time evolution and the matter evolution can be done through several numerical relativity codes that are publicly available, like the Einstein toolkit, Spectre, and Dendro, and there's many more. In our research, we use Einstein toolkit. In particular, people who are familiar with Einstein toolkit, we use the GR Hydro Thorn for the hydrodynamics. And we start with initial data generated using Lorine for the two neutron stars. Separated at a certain distance, by solving the TOV equation, and then we'll feed that initial data to Einstein toolkit to run the evolution and capture all the and then we capture all the observables like density profile over time, like the movie I showed earlier, and the gravitational wave signature at our simulation boundary, and so on. So now let's go into the matters of equations of state. So I've set up how we do the simulations. Now, the equation of state can be understood as a relation between pressure and density. So for any amount of density of nuclear matter, what is the corresponding pressure, degeneracy pressure it's going to contribute towards balancing the gravitational pressure. It can be seen as this plot on the right hand side, where the pressure is the y-axis, or log of pressure is the y-axis, and log of density is the x-axis. And as the density increases, naturally the pressure contributed by that amount of matter would increase. Now, the equation of state, as said earlier, is fairly well constrained at low densities at the moment. So densities below the nuclear saturation density is where, or half the nuclear saturation density is where we are fairly certain how the equation of state is going to be. At higher densities, it's much more uncertain because of the fact that there's the question whether nuclear matter transitions to quark matter or not, and how does that phase transition happen. So there's a lot of uncertainty in that, and that's also due to the fact that there's difficulties in lattice QCD through lattice QCD calculations. However, currently there exist many approximate calculations of the equation of state at these high densities. A couple of them I've listed over here. They're based on perturbative QCD methods by Kirkila et al. And Baim et al. In our work, we focus on the one by Baim et al., which is called the quark hadron crossover, or QHC19 A through D. There's 4 different values, so 4 different equations of state. So I'm going to call this QHC19, or simply just 19A or 19B from here on. So let me now describe how this equation of state goes. It's a cold equation of state at t equals 0, of course, for dense matter. Dense matter. At low densities, it's a simple, so low densities as in below twice the nuclear saturation density. This equation of state is a simple Togashi equation of state, which is an extension of APR. For densities above 5 times nuclear saturation density, where it's assumed that all the matter has transformed into quark matter, free quarks, the equation of state is calculated under the Nambu-Jona-Lazino model, where the quarks are taken into account in 3 of the 3 light flavors, and the gluon degrees of freedom are suppressed primarily, and there's some coupling constant freedom, some degrees of freedom due to the coupling constants between the quarks. So yeah, we'll get into that in a second. And so these 2 describe the low density and high density equations of state. The region in between these 2, from 2 to 5 times the nuclear saturation density, is the equation of state over there is approximated by doing a smooth fitting between the 2, smooth interpolation between the 2 regions, the region of hadronic matter and quark matter. And this region is going to be the phase transition region. And so this is how the equation of state is. Now, as I said, there's some degrees of freedom in the coupling constants between the quarks. And those have been quantified so far as different values of the coupling constants have been quantified as different equations of state. So QHC19 A, B, C, and D are all plotted over here. And if you try to squint a little bit, you will see that they have some amount of difference among them. A is the bottommost over here, and D is the cyan color over here, right on top of yellow. And yeah, all of them more or less agree fairly well with GW170817 observations of by LIGO, and all of them also cut off the basic necessity of having the highest nuclear neutron star mass to be 2 times the solar mass. So these reasons make this equation of state a very good contender for being for describing the dense matter or high density equation of state accurately. So now in our simulations, we do a little bit of adjustment of that equation of state to put it in GR Hydro or in Einstein Toolkit, because it doesn't take raw data as a raw equation of state as it is. What we do is do a piecewise polytropic equation fitting for a scheme for this equation of state. This was mentioned in some of the previous talks today itself, but I'm going to state it once again. So if you look at this plot on the right hand side, this is a plot for SLY. If you look at the red and gray curve, it is a plot of SLY equation of state. As the density increases, the pressure increases. Making it piecewise polytropic means that for different regions, so let's say this region from these dotted lines to these dotted lines, you make it a single polytropic linear equation of state. So this is a linear equation of state in this region, although this is in log scale. So that makes it an exponential equation of state. So, but the coefficients of the exponential would be different over here compared to the next region, and then the next region would have a different set of coefficients. And so we do this for the QHC equations of state as well. Let me go back to just stating the fitting conditions for doing the piecewise polytropic. The conditions are, firstly, the pressure should be given by this pressure density relation, a simple polytropic relation. The internal energy is given by this simple polytropic relation, and for the continuity of pressure, internal energy is imposed at each of these boundaries. At each of the boundaries where transition to a new piece happens. This is an adaptation. This is actually not even an adaptation. It is the same as Reed et al.'s scheme from 2009. So since I mentioned QHC, the important part of QHC is only at the high densities where the crossover happens and goes into the quark matter equation of state. So to simplify our calculations, we or not rather just calculations, to make our process more standardized, we assumed SLY equation of state for densities below the nuclear saturation density, just because QHC does not contribute anything over there. And for densities above there, we perform a three-piece piecewise fitting. So we fit that region with three pieces. And further, we also add the non-zero temperature contributions by a gamma thermal contribution. Now, so here I'm going to show how this the process, how our parameterization looks. So if you look at this curve on the left hand side, the black dashed curve line, vertical line, signifies the transition from SLY to QHC. So below the black line, everything is SLY equation of state in both these plots, and above it, it's the QHC. So in particular, left is for QHC 19b, and right is for QHC 19c. And so to find the best fitting parameters for making it piecewise polytropic, we of course let the three pieces, the gamma indices, be some degrees of freedom. So that those are 3 degrees of freedom. And further, we also let the boundaries where the transition to a new piece happens to be that to also be a couple of degrees of freedom. So here I'm just stating, and then we let our algorithm choose the best possible combination of these 5 degrees of freedom, so that the error is minimum when compared to the raw equation of state. And here I'm just stating the values that we achieve for QHC 19b and 19c. Now, moving on to just testing our equation of state compared to the raw data and our piecewise. Here I show the mass radius relations for 19b piecewise, for the equation of state 19b raw, which is in blue, and 19b piecewise that we made in red. And you can see they are in fairly good agreement with each other. Same goes for 19c. The 19c raw is in fairly good agreement with the 19c piecewise, given in pink, given in green, sorry. Now, moving on to the most important thing, which is the merger simulations and seeing the signature of the different equations of state. Here I'm going to be showing the merger movies of the mergers for 19c, for neutron stars described by 19c equation of state. On the left hand side, you will see the top down view of the merger. On the right hand side, you would see the edge on view of the merger, but a cross section of that. So you'll understand what I mean with that. So let me play the movie. Yeah, and you see that they're revolving around each other, going into and out of the plane. And we do the same simulation for 19b, and we see a similar effect, that they merge at the same time as 19c essentially. But as you see, 19c is staying in the hypermassive neutron star state for a very long period. 19b, on the other hand, the equation of state 19b, on the other hand, leads to a prompt collapse to a black hole. 19c, as you can see, it takes a lot longer to collapse into a black hole. So it's much later than 19b, which I'll show in a second. I hope this movie played well over Zoom. I'm not sure. but anyway,
Yes.
I'll upload my slides later on. But yeah, thank you. So now just comparing the 19B and 19C results once again. So I said the 19B has a much more prompt collapse to black hole. And that can be seen over here in the rho max plot and also in the gravitational wave signal, but we'll go to that later. So the rho max here shows that the two equations of state cases. So what I'm plotting over here firstly is the maximum density available in the entire simulation at any given time. So let's look, if you look at the blue curve, that's the maximum density in 19B evolution at any given time. So starting at t equals 0, this is the maximum density, and it's given in the units of nuclear saturation density. So it's about 3 times nuclear saturation density. But as you see, when it goes into more of the crossover region and beyond the crossover region, you start seeing differences in the evolution of these two. 19C has a much does not let a lot of density accumulate compared to 19B, where the density accumulates much more, and then there's a prompt collapse because the Schwarzschild limit is crossed, and 19C on the other hand stays in the hypermassive state for a much longer period. Same can be seen in the graph.
Atul, you have 3 minutes left, including
Yes.
questions.
Yes, sorry. So yeah, let me quickly wrap up and say that yeah, same can be seen in the gravitational wave signature as well. Pre-merger is same, post-merger is much different. Now over here, I just want to briefly mention that we are those results are preliminary. We should not say that that is conclusive at the moment, but we still need to perform some convergence tests, and our convergence tests look fairly consistent so far, but we are not done yet. And further, I want to the main point was I want you all to take is that this post-merger signature can be would be most likely be able to see we will be able to see through the next generation gravitational wave observatories like Einstein Telescope and the Cosmic Explorer, because their sensitivities are much lower. And LIGO on the other hand is, I don't have a plot over here, but it goes much above, and these high frequency regimes correspond to the post-merger signature. With that, I want to summarize. I'll leave my summary slide, and thank you all for listening and take all your questions.
Thank you, Atul.
Thank you.
We have time for a question. There is any questions for the audience? Let's see. I don't see questions in the chat.
Maybe I can ask a question.
Yes, please
Yes.
go.
Can you show again the mass radius relation of the equation of state?
Yes.
Okay, so from what I see at 2 point something solar, I mean the 19B barely reaches it's 2 point something solar masses.
Yeah.
The other one is a bit more stiff. What I want to say is just that probably you are still satisfying the latest nicer results, but the center of those results is somehow pushing to larger radii for objects having a mass of the order of 2 point something solar masses. I mean, I think that your curves are still passing through the limits that they published, although the center of the limits that they indicate is definitely quite significantly to the right of your curves.
Yeah, I'm aware of that, and I guess there needs to be some updating of the equation of state. So I remember, I know that the NICER is probably going a little more. The latest NICER is probably suggesting a little more on the right hand side, like you say. Yeah. But yeah, so so far this was the equation of state that we could work on. We don't have more updated data yet. And as to the cutoff, yeah, I feel like 19C is much more comfortably making the cutoff, and 19D goes even further above, but then it doesn't match with the LIGO constraints, and 19A is even below, a little bit below. So that is slightly on. It's not as good, but yeah.
Thank you.
Thank you for the comment.
Maybe
if there may be.
Oh yes, please. Yeah, please. Quick.
So yeah, could you please go to the gravitational wave slide where you have the frequency, the last, so the results on the right, are they just for the equation B or C? I can't.
Sorry, this is just for B, but for different resolutions.
Okay, good.
Yeah.
So you see such a second peak structure or something like that. Is this due to the phase transition? So
yes.
if you would compare it to the non-phase transition.
Yeah, we haven't done those comparisons yet, but as you can see visibly over here, so this the frequency that I showed you is for 19B, and 19B is the blue one over here. Non-phase transitions would almost certainly collapse as similar to 19B, right? Because they have the collapse would be much more prompt, whereas 19C is a much prolonged because it has the phase transition is much more pronounced in that case. So although I'm showing only 19B over here, 19C, I believe I should have made the plot, showed the plot over there of that over here as well. The features are much more pronounced for higher frequencies because those correspond to post-merger signature. Yeah.
There exists a little bit similar work, a very new thing by Ignazio Bombacci and David Radii.
Okay.
Do you know this work?
2000, yes, 2000.
No, just
last year.
Just 1 week ago or so.
Yeah, Viral Prakash and
yes, exactly.
Yeah. I've seen that. Yeah.
In comparison to their results, how are your results different?
I haven't looked at their results very carefully in this regards. Yeah, I should spend more time. I haven't gone to do that. Okay. But yeah, that is exactly what they're also essentially doing. The same thing. They're looking at the quark matter-based equations of state. So
yeah, and they have a temperature-dependent equation of state in. Yes. But the cold part, the equation of state looks very similar to yours, I have to say.
Oh, I see.
But okay. Yeah, so from a qualitative view.
Thank you, Matthias, for the comment.
Yeah, thank you very much for the comment.
Thanks, Atul. We move forward to the next speaker.
I had a comment.
Yes.
Well, keep in mind that the neutron star merging give origin to short GRB. And although the statistic is not very good yet, because we have some very good example, 9804, etc. And there has been one of last month, which is also possible. Therefore, keep in mind with Grant Matthews to try to see if you can see some of these overtones in the short GRB.
Sorry, can you repeat that?
Excuse me?
Can you repeat the last sentence you said?
You see some of the structure that you are finding in the short GRBs.
Okay.
Because some of them are, well, there are not many, but certainly they are real.
Okay.
Okay, thanks for the comment.
Thank you very much.
So we move to Shu Yan Lao. Okay, here you are. Oh, please start when you are ready.
Can you see it?
Yes.
Thank you very much. So thanks for giving me the opportunity to present here. So I'm Xuan Lao. I'm a PhD student from the University of Virginia, and I'm going to present this previous project with Professor Kent Yagi, my supervisor. And the results of this talk has already been published earlier this year. So if you're interested, please also take a look at it. So to get started, right. So I'd like to first briefly introduce our stellar model. So we're considering a hybrid star system. So basically a hybrid star shares the same global parameters like a typical neutron star. It has a mass of 1 to 2 solar mass and radius of 10 kilometers. And the difference is it has a quark matter core. And usually there are many ways people have proposed to distinguish a hybrid star from a neutron star. And Some of them requires measuring the mass radius relation and maybe look for the twin star scenario. And in our case, we want to focus on looking at the normal modes of a hybrid star. And to do so, we have to construct the hybrid star background model. And then after that, we compute the normal modes by solving the eigenvalue problem of the equation of motion of the internal motion inside the hybrid star. And lastly, we want to see how this affects the gravitational wave signal. So I want to add a little bit more about the confined quark matter core here. So we expect the quark matter to be in a color superconducting state, which means the quark matters, including the up, down, and strange quarks inside the core, we expect them to be able to form Cooper pairs of color charges, and this induces color superconductivity. And the phase diagram below is, roughly speaking, showing the different color superconducting phases we would expect that are possible in a low temperature, high density environment that includes the CFL phase, the 2CS phase, or the others. And here we are focusing on the CCS phase, which is the crystalline color superconducting phase. This phase is interesting because it is expected to exist as a solid, and we expect it to have a rather high rigidity, even like several orders of magnitude more rigid than a typical neutron star crust. And we expect it to give some interesting properties in the in-spiral stage during the binary hybrid star in-spiral signal. So in order to construct the background model, we consider the hybrid star equation of states, and we have to construct them by joining the normal neutron star equation of states at low density with the hybrid star with the quark matter model at high density. And for the quark matter part, we consider the modified back model, which is first used by Mark Alford on 2005. And this model basically describes the grand potential of the quark matter as a quartic function of the average quark chemical potential. And this model is a phenomenological model which depends on three different phenomenological parameters: the back constant, the A4 here is a constant that models the effect of the Qcd coupling constant, and A2 here is the effect that takes into account of the finite strange quark mass and also the color superconductivity in a color superconductor. And between these two phases, we assume there is a first order phase transition, which means there is a density gap between these two phases. So with that, we construct a total of 10 different hybrid star equation of states. And in below, we are showing the mass and radius relation for this hybrid star equation of states shown in dashed lines, and also the corresponding hadronic matter equation of states, which we denote as HEOS. And as we see, if when there is a quark matter core appearing, it actually softens the equation of state, and it supports a lower maximum mass for the system. And we classify these equation of states based on their transition pressure. So we have the high transition pressure model, which the transition pressure is beyond 10 to the 35 dyne per cm squared. And we also have the lower transition pressure equation of states, which the hybrid star starts to appearing at relative low mass. And among all these models, we require that the maximum supported mass by this hybrid star equation of state has to exceed the current observation bound roughly. That is larger than 2 solar mass, and the radius for a 1.4 solar mass hybrid star has to be smaller than 13.5 kilometers. So the last piece of our background model is the rigidity of the core. And for that, we'll need the relation between the shear modulus and the other thermodynamic parameters. And here we adapt the model from Radii et al. On 2007, which they studied the crystalline color superconducting phase and computed their shear modulus, which relates it with the chemical potential mu q here, and also an extra parameter delta here. It is the CCS phase gap parameter. So basically, this gap parameter, roughly speaking, is giving us a the coupling strength of the Cooper pairs inside this color superconducting phase. All right. So up to this point, I've described how we construct our EOS model and how we construct our background model. And now we want to look at how this model can give us some detectable signal in the gravitational waveform. So as we all know, a hybrid star or a typical neutron star consists of a rich spectrum of normal modes. Something like a coupled spring mass system depends on the normal modes are some natural frequencies that depends on the spring constant and the masses of the system. And in the scenario of a binary hybrid star in spiral, the companion star can exert an external tidal force. And when the tidal force has the orbital frequency that matches with the mode frequency, it causes a resonant effect. And this during this, a large amount of orbital energy can go into the internal motion, that is the normal mode energy. And this can cause a phase shift on the orbital motion. And hopefully this orbital phase shift can be detected through gravitational wave signal. And in this study, we focus on one of the particular normal modes called the interfacial mode in hybrid stars, because this interfacial mode is a unique feature in a system with an interface. By interface, we mean there is some discontinuity in either the density or the shear modulus of the interior. And in our case, we have both of these discontinuities. So another reason why we look at this interfacial mode is that it has a relatively low frequency for the various equation of state we consider. The frequency of this mode usually lies between several hundreds to 1,000 hertz, and which means the resonant frequencies might probably lie within the in-spiral stage of the binary hybrid star. And also, this particular mode couples rather strongly with its companion. That means we expect it to give a rather strong signal in the orbital phase shift. So next, I'm going to explain how this orbital phase shift enters the gravitational wave in spiral waveform. So for a binary neutron star or binary hybrid star waveform, we consider 3 different contributions in our waveform. First, we use the IMR Phantom D model, a phenomenological model for the in-spiral merger ring down waveform for a binary black hole system. And we also consider the finite size effect due to the existence of equilibrium tides. And lastly, we insert the interfacial mode contribution, which also enters as a phase term in the gravitational waveform. And here we have made some assumptions on this extra phase term. We assume that the interfacial mode enters into the gravitational wave phase only only during the resonance, and it happens at a very short period of time. That is, we have ignored a diabatic effect before and after the resonance. From this, we can derive the extra phase shift due to I mode as this formula, which depends linearly as the overall phase shift on the orbit. And it also depends on a Heaviside step function, which indicates that this phase shift happens only after the frequency sweeps through the resonant frequency of the I mode. So within this waveform, there are a total of 11 parameters, something like the chirp mass, the mass ratio, the spins, but we're focusing on only the interfacial mode parameters, which are the resonant frequency and the overall phase shift. So next, we perform the Fisher analysis to try to see how detectable these I mode parameters are. In particular, we look at the overall phase shift on the orbit. So through a Fisher analysis, we compute the Fisher matrix of the above waveform, and the inverse of the Fisher matrix gives us the measurement error of these parameters. So an interesting thing through the Fisher analysis is that we find that the error on the phase shift is almost independent of the value of the phase shift itself. That means if we have fixed the other non-I mode parameters, this measurement error depends only on the I mode frequency. So with that, we can actually plot the measurement error as a function of the eye mode frequency for different detectors. Here we have selected the advanced LIGO detector and also the Cosmic Explorer, which is a 3rd generation detector with a much higher sensitivity than the current 2nd generation detector. So from this plot, we are able to illustrate in the parameter space which kinds of eye modes are detectable using gravitational waves. So basically, we set the measurable criterion for this orbital phase to be the measured values has to be larger than the measurement error, such that the fractional error is smaller than 1. And in that case, if we have an eye mode that lies within this region that is above the green curve, then its measured value is larger than the measurement error, and we claim that it is detectable. So the opposite is if it's below, then it is undetectable. So keeping this in mind, here I'm showing the major results of this study. So basically, we consider two different equal mass binary hybrid star system, one with 1.4 solar mass and the other one with 1.8 solar mass. And I'm showing here for each data point, it represents the interfacial mode for one particular equation of state that is constructed above. And I'm using different symbols to distinguish them with a different value for the CCS gap parameter. So as a reminder, this CCS gap parameter kind of tells us how large the shear modulus is. So, and also here I'm using different colors to distinguish their transition pressure. So for the magenta ones, they have the high transition pressure, and the black ones, they have the low transition pressure. And one remarkable thing about this figure is that we find that even for the current 2nd generation detectors like advanced LIGO, there's possibilities that we can detect some of the eye modes at the phase shift, overall phase shift of some of the eye modes if the transition pressure is low enough, and also if the gap parameter is large enough, that is the shear modulus is large enough. And also this detection favors the interfacial mode with a lower frequency, lower resonance frequency, judging from the detectability threshold curves. And as we increase the mass of the system, this low transition pressure equation of state, the eye mode becomes less detectable, but the intermediate ones becomes more detectable if we have a 3rd generation detector online. So this basically summarizes our findings. So basically, we find that the interfacial modes of the hybrid star systems range from around several hundred to 1,000 hertz. And it has, for some of the model, it has quite a significant orbital phase shift on orbit, which makes them even detectable with the 2nd generation detectors. And if we look into the data closely, we find that the eye modes are more detectable for models with a lower eye mode frequency and a low transition pressure, but with a larger shear modulus. So this basically it for my presentation. Thank you for your attention, and I'm happy to take any questions.
Thanks a lot for your talk, very interesting. And yes, please, if there are questions. So if I understand correctly, what you are suggesting is that it will be possible to detect these frequencies, these emissions, as a sort of periodic emission waves. Do I understand it correctly? I mean, we can study neutron stars and under certain conditions, we expect that there will be an emission of fractional waves of this type, having these frequencies. Is this what you have in mind, or I misunderstood?
I'm here suggesting, I'm not sure if I'm getting it correctly, but
I mean, what you're speaking about is not a transient. Is a signal that will be emitted by a single neutron star that is spinning at a certain frequency, or what?
Oh no, it is actually a signal that enters the binary neutron star waveform. As the this interfacial mode kind of resonates, then it causes the orbital energy to shift into the internal energy of the star. And this causes a phase shift in the overall binary motion. And this can be kind of observable inside the gravitational wave signal. So it is something about the orbit itself.
Okay, so I will see. So this is really a sort of, you observe this during the merger. But how easy it is to, because at the moment, unfortunately, I mean, we have not seen any signal in the post-merger. So how easy it is to understand that that particular feature will be due to this mechanism and not to some other mechanism in the post-merger?
So this feature, we expect it to happen during the in-spiral stage. So it is the stage where while the signal is still relatively clean. And yeah, so we didn't consider the post-merger effects in this study.
Okay. Oh, there is a question by Jonas, please. Is there a question? Jonas, can you please ask your question? Maybe it was Jonas? Maybe it was not.
Yes, I see. It was your hand. Okay.
Okay. Okay, so I understand. So you are claiming that this will be a clear modification of the in-spiral signal. Is correct? Is this the point?
Yes, that's right. I didn't make it very clear, but yeah, we're focusing on the in-spiral part of the signal. And in fact, we have truncated the signal at the east core frequency, the innermost stable circular orbit frequency, which we assume beyond that it is a merger. It enters the merger phase, and where the signal gets messy, and this I mode is actually not detectable beyond this frequency.
Okay. If there are no other questions, I thank you for this very interesting and stimulating talk. And we can move to the next speaker, which is Matthias Nauske.
Thank you.
Thanks again.
So you can see the transparencies, or
yeah.
So today I will focus on the post-merger phase and what the remnant and the material inside the star is doing. So we are using numerical simulations in full general relativity, where the 3+1 decomposition of space-time is used with the lapse function alpha and the shift vector beta, which is described here. I will also look now at the post-merger phase, and here on the right-hand side of the Einstein equation, where the energy momentum tensor enters, I will also look what the possibility of a hadron quark phase transition could do, where you have here the temperature and here the density, and when the two neutron stars merge, the whole space of the Qcd phase diagrams populated in the interior of the remnant, and this I would like to show you. Here's just the in-spiral phase, where I will not talk about here really the latest point of the in-spiral phase. Here you see, for example, this lapse function alpha of the two stars, and here you see the phi component of the shift vector beta. And because of the movement of the stars here, space-time is dragged with a star, and this is the frame dragging of the thing which enters into 3+1 decomposition. When the remnant is created, then the frame dragging and the alpha changes a lot, and I will talk about that also. Here you see now the gravitational wave emitted beginning from the latest point of the in-spiral, where the 2 neutron stars, here you see the density in units of normal nuclear matter. Here is the so-called ALF2 equation of state from Alford Hughes, where a phase transition to the quark-gluon plasma was included at 3 times normal nuclear matter. But this phase transition in this equation of state is so smooth that you can't see anything in the equation of state. But I will play the movie, and you see here the post-merger phase, the double core structure first, and now here the red contour line marks 3 times normal nuclear matter. You see that the density in the interior gets denser and denser above 3-4 times normal nuclear matter, where mixed phase and pure quark matter might be possible, and then it collapses to a black hole. We want to look now at the temperature and what the density and temperature is doing, and also what the fluid elements inside the star are doing. And we are transforming now in a so-called co-rotating frame. So we are jumping on the 2 neutron stars and rotate with them. This one does by rotating the system with the instantaneous gravitational wave frequency emitted here. And here you see just so the 2 neutron stars, here you see the temperature of the 2 neutron stars in the in-spiral phase. They usually rotate, but in the co-rotating frame, they are not rotating. And we are now focusing on this strange temperature structure over here. We're trying to understand that. First, using hadronic models without a phase transition. So, and additionally, we have put so-called tracer particles here in, which tracks the fluid motion. Here is the density plotted, and here's the temperature plotted in the equatorial plane. We are now right at merger time, and we are looking what the interior of the remnant is doing in the post-merger time. The double core structure first, then here the particles moving around in circles over here, and these are the positions where the hot temperature, 2 temperature hotspots occur. Yeah. However, the temperature in the interior is not so hot, as you can see. In the interior, it is really dense, but it's not so hot. Yeah. In the center of the remnant. But then after maybe 10 milliseconds, this hotspot smear out to a ring-like structure over here, which is more a donut on the equatorial plane with a really still very high temperature ring here, which sits roughly at 1.5 normal nuclear matter. So inside the remnant. So we have to understand why this temperature ring and these temperature hotspots come. And there, but before we will do that, we look at the same simulation, the same tracers and so on in the Qcd phase diagram. So this is a purely hadronic model. It's the LS220 equation of state, which you saw. And here you have the temperature of the material. Here you have the density of the material, just at a point a little bit after merger. And the color here visualizes where the matter in the remnant is. Yeah. For example, this region here is really in the core of the remnant. Yeah. And these regions are at 10 kilometers outside. So now looking the same simulation now in this T versus rho diagram. This is the wild post-merger phase, the transient post-merger phase. Yeah? And it populates here up to 50 MeV, 60 MeV, and the density in the interior is not so hot as you can see, and it gets denser and denser. The particles, the tracer particles, follow special curves here, and the maximum here corresponds to this ring-like structure now. Yeah, this is the position of the maximum temperature. Okay, I have to speed up a little bit to understand why this occurs. One has to understand the differential rotation curves inside the hypermassive neutron star. When you look at the 3+1 decomposition and look how the angular velocity is written there, it's a Letz function times the phi component of the velocity of the particles, but minus this frame dragging component, which we have also saw today in the planetary talk, that in respect of the Earth, there is a frame dragging, but in the interior of a hypermassive neutron star, this frame dragging is really huge. But why I'm talking about the rotation curves, this is to understand the temperature structure. One can easily see it with the rotation curves. Here I plot the omega, here the temperature, now not in a co-rotating frame, and you see exactly where the maximum values of the omega occur, and the interior is not rotating so fast, and exactly at this point the temperature hotspots come. This is independent of the equation of state, and this gives here these rotation curves. The inner part of the remnant is not rotating fast, and then one has here the maximum, and this maximum value of the rotation curves corresponds now to the so-called F2 frequency, which is emitted, which is the main frequency after 5 milliseconds emitted from the hypermassive neutron star. This was a hypermassive neutron star, but now we are looking what phase transitions are doing. So one can look at gravitational wave signatures of a phase transition within the late inspiral phase, but I will focus here on the post-merger phase, and there are in principle 3 kinds of phase transition signatures, and I will first focus on the so-called phase transition triggered collapse. But the main question is, can we detect the Broglie plasma with gravitational waves in the near future? And I think yes, we can, and there are possibilities with a little bit luck, but for sure with the next generation gravitational wave telescopes. So the phase transition triggered collapse scenario, here you see the emitted gravitational waves, red with a phase transition, black without a phase transition. And a lot of articles, not only this article from our group, shows now that if such a phase transition occurs, one sees a earlier collapse to a black hole with a different ring down phase, but you see here also a phase shifting, and this I will explain, and I will now show you the movie how the situation with a phase transition looks like. So this is just the merger part, the violent transient post-merger evolution. Here again, what the remnant is doing in the temperature versus density plane. These are the temperature hotspots over here, which contains deconfined quark bubbles. Maybe I can stop here, just right here. These are the temperature hotspots, and inside the temperature hotspots, as you see in the background where the quark fraction is visualized, these contain a little bit quarks for the simulation with a hadron quark phase transition, and due to this, this phase difference comes. But the main thing is going to happen when the inner cold part meets the first order strong phase transition over here. And you will see it now in this case, no stable hybrid stars are possible, and the temperature in the interior is heating up, and then it collapses to a black hole. And this is the last snapshot of our simulation before the code tracks the apparent horizon. And it looks, and here's on a logarithmic scale. So this is 10 times normal nuclear matter here in the interior of the star. And this is a little bit more outside here, but it's collapsing now. And this is the last picture. Yeah, we can go again into the different, maybe to understand it here. So the interior is now also heated up and contains deconfined quarks also, yeah. And this is the last picture. It looks a little bit like a strange bird where with a deconfined head where strange quark matter is present. But then here in the wings and here at the end, mostly hadronic matter is still there. If you plot it not as a function of density, if you've plotted in the chemical potential, you see now the following. Just to explain you, this is a similar thing as Penrose discussed in his Nobel Prize article. So the matter is now collapsing, the trapped surfaces are formed here, and this is now the last picture what an observer, an outside observer could see. And if you plot the strange bird here as the chemical potential, it looks like such a swan picture over here. So this is the last picture. What an outside observer sees is the frozen picture of a dying swan, one could say. I don't know how much time I have. You will interrupt me, but I want just at the end talk about the so-called delayed phase transition.
You still have some 3 minutes, three minutes.
Okay, perfect. So here we have a model where we have a mixed phase region over here. And from 4 times normal nuclear matter, we have a pure quark phase modeled. And we see here is the merger time. Here the simulation without a phase transition, and 2 simulations here with the different resolutions with a phase transition. And in this case, it collapses not to a black hole. It collapses to a so-called hypermassive hybrid star. Yeah, and at this star we want to look at. So this is the situation over here where both simulation with and without phase transition are more or less the same. The density structure of the equatorial plane, the alpha and the frame dragging beta phi component. Now we are looking here at these kind of things, and there you see a huge difference here. Here, with phase transition, the interior contains quarks. The alpha is really, the space-time is deformed much more. The frame dragging is much more because this star rotates much faster, this hybrid star over here. Now we look at this point over here. Here, with phase transition, density, the omega profile, the differential rotation profile, the frame dragging frequency, and here the emitted gravitational waves. And you can see it by eye that you get a higher frequency here emitted from this simulation with a phase transition. And this you can see as a shift of the F2 peak here and which you see here also in the frequency over there. I only talked on the equatorial plane, but you can see here, one can also look at the temperature and the other structures on the XZ plane also. Okay, with this I want to end. Thanks a lot.
Thank you very much, Matthias, for this very interesting talk. And of course, questions?
Well, Matthias, I am fascinated by the quality of the analysis, and especially all this frame dragging and so forth. And I really would like to ask you to use this very advanced analysis in the case of two binary neutron star merging forming a black hole, which we have the data of a short GRB in 090510. Please look at that, and especially there is the prompt emission, which lasts a fraction of a second, which you should be able to mimic. But the most interesting case in that source is that there is also an afterglow lasting of the order of 10 to the 4th second, which could be generated by the structure. If you like, we can send you the reference, but it will be fantastic to implement this new analysis you are making on a real case, because there we have seen the short GRB certainly is a binary neutron star, and we have data still unexplained for the long-lasting following up for 10 to the 4th second. It will be very exciting. We will send you the material.
Oh yes,
But
please. Yes. So I have to say, since the last 2 years or so, I was mainly focusing on gravitational wave because it was new, and I did not find the time look into these short GRB structures, and probably one could find there something already in. Yeah. So thanks a lot for this comment.
Absolutely.
Jorge,
And
please.
congratulations of the beautiful work.
Oh, thanks a lot.
Thank you. Thank you. Yes. Okay. I joined this comment. That was a really beautiful presentation. Really very beautiful and very precise work. On this, I'm a little bit confused. This peak of the temperature is a bit strange because it's in the interior of the dense object. Because
yeah. So.
May I add something? Sorry, I didn't finish. Sorry, just to emphasize, to focus a little bit more on my question. In the case, for example, of white dwarf mergers, you see such kind of a structure when you see the peak of the temperature in the same place of the peak of the angular velocity. And this is just a region separating the uniformly rotating core with the Keplerian disk that's formed around. And this is a hot corona where the alpha dynamo is very effective and you develop strong magnetic fields. So, but this is the region separating the dense core and the disk. But here it's inside the dense regions, right?
Yeah, exactly. Here it is different. One sees in all of the simulation what we have, and also all the other groups see it also. Yes, that one sees first these temperature. So after maybe 3-4 milliseconds, one sees temperature hotspots, and these temperature hotspots are strongly at the positions of the angular velocity, and I can maybe just show you there where they appears. So this is the slowly rotating inner region, and the temperature hotspots appear where the sharp increases here, and later they smear out to ring-like structure. But this is in the interior of the remnant. Look, this is and comparing to density, it is depending on the equation of state and so, but at 1 to 2 times normal nuclear matter. So it is not out where the crust is, but it's also not inside the core. It is in between,
No, because I see here that after that you see the Keplerian tail.
Yes, exactly. This is the Keplerian. So and this is really outside. So no, the temperature hotspots, 40, 50 MeV, really high. These are in the interior, but not in the deep core.
It is like a flare.
What do you mean by flare? It is maybe I can. It is like a hot blobs which are moving around, and later at 10 milliseconds or 15, they smear out to a hot ring-like structure. The interior of the hypermassive hybrid star is not so hot, maybe 10 MeV5, but then there is this hot ring at 1 to 2 times normal nuclear matter, yeah, which is 40, 50 MeV.
Matthias, if I'm not mistaken, correct me if I am wrong, in the calculations you don't include explicitly viscosity, but you have the numerical viscosity, correct?
Yes,
so
yeah.
It may be possible that the fact that the temperature rises so much in that area is because in that area you have a very high differential velocity, and therefore even numerical viscosity starts dissipating the differential velocity. Am I wrong?
No, I don't think that it's because of numerical velocity.
Viscosity.
Yeah, and also all of the other numerical groups sees that Bauswein, these are at the position where the low rotating inner region and this highly rotating ring meets to each other. There it gets hot.
Yeah. Thanks a lot. Thanks a lot. It's very, very interesting, and I hope that we can discuss soon together again. Okay, thanks again, and we can move to the next speaker, which is Riccardo La Placa. Please.
Hello.
Hello.
Just share my screen in a second. Let's see if you can see it. Okay, can you see the presentation?
Yeah.
Very well. Hello, everyone. So I'm a PhD student from the University of Rome, and today I will be presenting you a new method that we developed to try and constrain the radius to mass ratio of neutron stars from X-ray spectroscopy, and in particular from the occultation of the accretion disk around these neutron stars. Now, I'm sure I don't need to stress how important it is to put good constraints of the equation of states of neutron stars to this audience. But let me just remind you that in order to put tight constraint on the equation of state, so that we can actually discriminate between different equation of states, we need to put constraint on the mass and radius of neutron stars to a precision of 5% or better, pretty much. Now we have precise measurement of some masses of neutron stars, both in binary and isolate systems. But radii, as of now, are still a little bit more elusive, let's say, with precisions that are no better than 10% in most cases. The method I'm going to present to you now is based on the X-ray spectroscopy in low mass X-ray binaries, which are the systems in which matter from the companion star is flowing throughout the Roche lobe and starts accreting on the compact object by forming an accretion disk. Now the spectrum, the X-ray spectrum of these systems is characterized by a steep power law, and that is coming generally from a hot corona or torus that could be around the neutron star, above the neutron star, or even from the surface of the neutron star. There's still some uncertainty there. And also the so-called reflection spectrum, which is basically reprocessed emission coming from the corona that hits the disk and then is reprocessed and sent to us. among the characteristics of these reflection spectrum, one of the most important ones is the iron line. The iron line is a fluorescence K alpha line that is peaking at around 6.47 keV. And it has been seen since the very first years of X-ray spectroscopy. And in the late 80s and the beginning of the 90s, we finally understood that it was actually coming, this large shape of a line, which in the laboratory emission should be a simple delta, was coming from relativistic effects. In fact, since matter in the disk is flowing at velocities that can reach even more than 10% the speed of light, it is important to account for all gravitational effects on the emission of these disks. And in particular, since we have a disk that, of course, we'll see as having one side which is blue shifted coming towards us and one side which is red shifted because it's turning away from us. In Newtonian gravity, we would have a simple two-peaked shape. Now, the two shapes here are just for different area, different radii in the disks. But if we add special relativity and general relativity, what we see is that the actual shape becomes more asymmetrical, and the whole profile gets redshifted by gravitational redshift. Now, the resulting profile is, as you can see, very asymmetric, very broad, and it is characterized by a blue wing and a red wing with a kind of trough here that can or cannot be present depending on where the gravitational, the outer disk radius is. Now, this profile has been an exceptional tool in X-ray spectroscopy, since it can give information on the spin of the compact object. It can give information on the inner and outer disk radii. It can give information on the inclination of the system, and on the, of course, on the energy line, which is a proxy for the ionization of the disk. So it's no wonder that it has been used extensively in the last 30 years. But there's one small detail that no one had accounted before. And that is the fact that simply through geometry, you get that while most of the trajectories, most of the points on the disk will be observed by any observer at infinity, also thanks to some gravitational light bending, there will be some trajectories right behind the neutron star with, I mean, with respect to the observer, of course, that will be intercepted by the neutron star itself. This means that a small area behind the neutron star will not be observed, but the fact that this small area is not to be considered when modeling data had never been taken into account before. Now, we developed a code that can define which are the points on the disk that are not that are occulted, and through that we can we can define which is the occulted area for any configuration, and you can do it for one system, you can do it for many systems, and of course you see what you expect. You see that for higher inclinations and for larger neutron stars, you get larger occulted areas, and this of course makes sense. But once you can create the area, once you can define which is the occulted area, you can also define how the fact that you should not account for this flux, for the flux that's coming from this red crescent, should impact your iron K alpha profiles. And we see that the loss in flux, you see here 3 cases for larger and larger neutron stars, and in green here you have the unocculted cases, compared with the purple ones, which are the actually occulted cases by neutron stars of 6Rg, 7Rg, and 8Rg. This because the occultation only depends on the radius of the neutron stars in terms of the gravitational radii, so in terms of the mass of the neutron star. And you can see that the difference is fairly small in absolute terms, because it's ranging from 2% of the peak to around 7% of the peak. But the most important thing is here, not the actual, not the absolute loss in flux, but the relative loss in flux. And here I plotted the ratio between the occulted and unocculted case. And you can see that since these, and this is then normalized to the average value of the ratio, and you can see that since this is not a flat ratio, this is a signature that you will see in the spectra, provided you have enough sensitivity, and that, so it will leave a signature on the spectra which is not simply renormalizable. It's not a simple uniform loss of flux across the whole iron line profile. And you can see that it is also fairly stable, even if you go to lower, to smaller neutron stars. Now, since we have this model and we have this code, we can decide then to fit some actual data if we find an interesting enough source. And actually we found a very good candidate, which is 4U1636-53, a long name, but it's a low mass X-ray binary which hosts a neutron star whose inclination was consistently reported to be high, and the inner disk radius is very close to the ISCO. It also has a quite good flux so that the signal is easily detectable, and a broad iron K alpha line. We analyzed some 100 kiloseconds of observation with NuStar, but unfortunately the signal to noise ratio still isn't good enough to accurately constrain the radius to mass ratio through this method. Therefore, we decided to point our heads onto a different direction, and we decided we would try to see what could be observable with the new generation of instrumentation. And in particular, we went looking for EXTP. Now, some of you may have already listened to the presentation in the past days about EXTP, which will be an amazing instrument. We're talking about an effective area which is 1 order of magnitude larger than current and past instrumentation, which will be a game changer for many fields of X-ray spectroscopy. But although, yes, it's not sure whether it's going to launch soon enough, but still it's going to be launched within the decade. And so we decided to simulate how we would see the same system. So we used the same parameters that we could see in our fit, but simulate those observations with the EXTP response matrices. And what we find is, frankly, kind of amazing. Just to give you an idea of the huge signal to noise ratio that EXTP has, this is the residuals that you get if you don't account for the iron K alpha profile. And you can see perfectly the shape of the iron K alpha line with, I mean, this is 200 sigma, so this is a very high quality spectrum. But if you, instead, if you do turn on, of course, your iron K alpha line, and you turn off the occultation for a moment, you see that still you have some residuals. And this means that you could actually try and measure the radius to mass ratio of neutron stars with this instrument. To what precision? Now, we've run almost 30 simulations for this source, but changing the inclination and the neutron star radius. And we saw that for every single simulation that we run when the inner disk radius was exactly at the surface of the star, we could recover the radius of the neutron star to better than 5% accuracy. Actually, in almost all cases, it was better than 3% accuracy. 3% precision, of course, sorry. And, but we also wanted to make things a little bit harder, and we decided to try it when the inner disk radius is a little bit further away from the surface of the star. So it's the radius of the surface of the star plus 1 RG. And still, in almost all cases, we could find, with the same precision, the radius of the neutron star. And in the few cases in which we could not, this one, and this one, we still managed to find constraints on the radius of the neutron stars, upper limits on the radius of the neutron stars, that were tighter than we could have found if we had only looked at the inner disk radius as a maximum radius for the neutron star. Now, this means that in terms of our beloved master radius equation of state graph, for example, here you can see in orange, these are two different methods that even with the XCP again, will put some constraint on the neutron star radius. And you can see here in the dotted orange line gives you constraint through photospheric radius expansion during the thermonuclear X-ray bursts. And in solid orange, you find the pulse profile modeling. While if we add for example, a measurement of the radius to mass ratio of 6 plus or minus 3%, we obtained this green area here, which is actually, it is actually much, much better than we can find nowadays. So we are confident that with the new generation of instrumentation, especially XTP, but probably even with Athena, we will be able to put some strong constraint on the neutron star radius to mass ratio, and therefore by reflection on the equation of state of neutron stars. Now I'll just summarize everything. I think I'm at around 16 minutes. Iron K alpha line profiles have already proved to be one of the most important probes of systems with in the strong gravity field regime. And we have developed a new subroutine, which is called ChatDisk, to fit these broadened profiles by that can be used in the most common program for X-ray analysis, which is XPEC. And it uses a very accurate approximation of the photon trajectories, which makes it very fast and doesn't need to rely on very big tables of pre-compiled and pre-calculated photon geodesics. Through the new generation of instruments, I cannot stress this enough, we should be able to measure it for high enough inclination and closed disks. This will help us constrain the equation of state. And we also actually developed a convolution version of the model, because instead of using it to produce one single line, you could do it to convolve relativistically the whole spectrum. But unfortunately, while doing that, we discovered that many convolution models, among which some of the most widely used, are actually affected by spurious effects that introduce some uncertainties of 5 to 10%, and which can be a problem not only for our model, but actually for all models that are currently relying on those convolution codes. And with this, I thank you, and it's been a pleasure.
Thanks a lot for this very informative talk. And I see that there are a couple of questions. First one by Jonas Pereira, please.
Yes, you guys can hear me now, right?
Yes, yes.
Okay, great. So my question is about the uncertainties related to solely modeling. Can you estimate them? Because I think that for modeling accretion disks and all the complexities there, it would lead possibly to large differences in your observables, right?
Sorry, I couldn't get the first half of your question.
Yes, it's related to how much modeling itself affects the results.
Yes.
And if you're able to estimate that.
You mean modeling in terms of the other components in the disk?
Of the things that are happening in the disk, because there is a lot of physics happening there. You have dissipation, you have many effects. How would they contribute or how would they contribute to the uncertainties at the end?
Yes, of course. Well, those are of course problems that are in a sense above any current of estimation that you could manage to do, because of the problem that is I mean, you can try and model that through codes that do prepare the full spectrum from disks, even in let's say complex configurations of the disk. I mean, I don't know about maybe very turbulent disks or anything. This is of course an approximation, and I mean most models work with the thin disk approximation in a sense, but there are some that do model better the inner physics of the disk. In those cases, you could in principle convolve the shape of the emission from the disk to find the radius to mass ratio over the whole spectrum. In that way, you make a more how to say self-consistent portrait of the physics within too. But I think that mostly depends also on the model you're choosing. So I don't have a proper a quantitative answer to your question. I'm sorry, but that really depends on what model you use in the beginning, let's say, as a basis. And unfortunately, I have no estimate for that.
Okay, thank you.
Okay, I think that Jorge maybe had a question.
Thank you. Yes. Ricardo, so your model of the disk is based in the Schwarzschild geometry. So yes. It means that you are neglecting effects of rotation, for example. And yes. And the second thing is you assume that you know the mass, right, of the star, because otherwise you don't know where the inner radius is, since you are assuming Schwarzschild metric. So yeah,
but that's really not the case, actually. I mean, because the whole profile depends on the radius only through its radius to mass ratio. So it's always the radius in terms of the gravitational radii, because it's all gravitational, it's all GR effects. Now, of course, if you want to go out of GR, that's going to be a different problem. But no. In general, in GR, this is all accountable because it's all scaled through the mass of the object, so it doesn't really matter. As this is why generally what you find, even with the calculation with the current measurements, we only rely on the inner disk radius. You only find the inner disk radius in terms of gravitational radii. So you're always going to have something like this line here. Okay.
Yeah. Yes. But Ricardo, there is only another thing that I would like to say.
Oh, yeah, sure.
Is the effect of rotation, because even in fast, in relatively moderate rotation, because there is some population of X-ray binaries, low mass X-ray binaries, in which the neutron star is expected to be fast, or the order of 500 or 600 hertz of frequency, or rotation frequency. In that case, then you will have a degeneracy, because when you have that, actually what you consider, for example, in the non-rotating case, that the one disk is on the most of the way to it's separated from the surface. For in the case of rotation, it isn't.
Yes,
so
that is true. That is true. But we also tried to see that, because actually the fact is, a disk is separate from the surface. It doesn't reach the surface only if the neutron star is smaller than 6Rg, of course, in the Schwarzschild metric. But if you get to, if you have a neutron star which is much smaller than 6Rg, you would not get occultation anyway, because at that point you don't get that much of a shadow. But even if you have a neutron star which is rotating, we tried this. We tried this adding both the ellipticity of the neutron star by, and we added also Hartle and Thorne, a Hartle and Thorne metric for the exterior of the neutron star. Even for relatively fast spinning neutron star, as you said, like 500 hertz, you could find that if you don't account for the rotation of space-time, what you get is you would only see in Schwarzschild metric. So let's say you would only see the polar radius. You would detect with the occultation, you would detect the polar radius. But if you do account for that, you actually detect the equatorial radius. So, for example, if you have, I don't have a plot for that.
Ricardo, we are still running a little bit late now. I think that.
No, yes, it's okay with me. I understand what he's trying to say. That's okay.
It's actually really fast. I don't think I have a plot for an ellipsoidal geometry, but you can imagine like this. If this is a little bit squashed on the pole so that it is smaller on the pole, okay, you would find, actually you would detect with the occultation, you would detect the radius to mass ratio of the equatorial radius, okay? This is what we found by simulating it and fitting those data.
Yes, that's okay.
Of course, you introduce a degeneracy, because you introduce the degeneracy of the fact that you have that it could be a fast rotating smaller star, let's say more oblate star, or it could be a Schwarzschild spherical star. But still, it's nice to know that it holds up in a certain way.
I'm sorry to interrupt you, but really we are running very, very late now. So thanks a lot for this. It was extremely important. But,
thank you.
Okay. So we move to the last speaker of today, which is Dawood Karkevandi. And thanks a lot, Ricardo, for the talk. And please, Dawood.
Yeah. Can you see my screen?
Yes, thanks.
So, how much time do I have? Because if we are, I think
50 plus 5. I checked. We are shutting down at 7:45, so we are still in the safe area.
Okay. So first, thanks other speakers for the informative talks and also the coordinator of this session. As you can see, my talk is about bosonic dark matter in neutron stars and gravitational waves, which has been done in collaboration with Soroush, Violetta, and Oleksiy. As you can see here, we face with 4 different terms: bosonic, dark matter, neutron stars, and gravitational waves, which through this talk, I will explain the relation between these terms. I mean, we have several observational evidences for dark matter, different candidate for them, and we know that neutron star as a in fact densest object in the universe, we can have dark matter inside or around it, and by having different observational techniques, so we can probe this in fact question that how dark matter can affect the neutron star structure. So the first question that will pops in your mind is that how dark matter can exist in neutron star, or can accumulate in neutron star. As you can see, for example, there are different scenarios in this regard. For example, accumulation of dark matter by a star or neutron star during its lifetime, which my colleagues has done a very nice estimation about for this case. For example, neutron star exists in the dense halo region of dark matter or passes through it, or hypothetical object like dark star that can be as an accretion center for baryonic matter, dark matter production in neutron star, or dark matter captured by neutron star in a binary system, including dark star or dark star neutron star merger. However, regardless of how much and how dark matter can exist in neutron star, when we have dark matter in neutron star, we call it dark matter admixed neutron star. And in terms of the dark matter model, we have two different, in fact, cases. One is the asymmetric dark matter, which is our considered model, and the other one is self-annihilating dark matter, which the most important observable quantity is the luminosity and effective temperature. However, for this one that we have stable dark matter, mass radius profile and tidal deformability are the most useful observable quantities. And for this case that we have asymmetric dark matter, there are two models. One is the single fluid dark matter admixed neutron star, and the other one is two fluid dark matter admixed neutron star. For a single fluid, we describe the whole object by just one equation of a state, in which we consider the dark matter baryonic matter interaction. However, for this one, which is more preferable in this context, dark matter and baryonic matter interact only through gravitational force. So when for this case, we have to have two equations of a state, one for baryonic matter and the other one for dark matter. In our investigation, we used for baryonic matter equation of a state the EOS with induced surface tension as a beta stable matter, which is consistent with different observational and experimental results and is derived by my colleagues, and it's a very new and modern equation of a state. And for dark matter, we see self-interacting complex scalar field as a bosonic dark matter with self-interaction, which is mainly used as a boson star equation of a state with repulsive self-interaction defined by a lambda 5 for potential, and was first derived by Kolpe and her colleagues. And the free parameter of the dark matter model here is the boson mass and the coupling constant, which in our research, we mainly focus on sub-giga electron volt dark matter and the strong coupling regime, which is around in the order of 1. And this equation of a state is also used as a dark star in these references. So for all the people who are familiar with neutron star researches, we know that when we want to investigate the structure of compact objects, we have to go through Tolman-Oppenheimer-Volkoff equation, which in this case we have, because we have dark matter and baryonic matter fluids which interact only gravitationally, we have two fluid dark top equation, which you can see here, the derivative of baryonic matter part in terms of radius, and for dark matter part, here is the pure baryonic part and the pure dark matter part, and the mass and pressure here have contribution from both of the fluids. Here you can see MB and MD, and here PB plus PD. And now by having two equations of a state for dark matter and the baryonic matter and the two fluid top equation, we can go through to investigate the structure of dark matter admixed neutron star by selecting two central baryonic matter and dark matter pressure, which you can see here, PBC, C here means central, and PDC. And then we start our calculation from the center of the object. And the most important question here is that the pressure of which of the fluids gets zero first. There are two possibilities here. One is that if the pressure of dark matter gets first zero, that we have a structure named DM core. In fact, we have a core which is mixture of dark matter and baryonic matter, and from the radius that the pressure of dark matter gets 0, we have only a single Foytov equation which works with the equation of a state by baryonic matter, and so the radius is defined by the baryonic matter equation of a state named RB, and we call this a structure DM core. However, if the baryonic matter part gets, the pressure of baryonic matter part gets first 0, then we have again a core mixture of dark matter and baryonic matter. However, the radius of the object will be computed based on the equation of a state of dark matter, so we call it RD, and this structure is named DM halo. But the mass for both of the object is defined by the mass of the baryonic matter part plus the mass of dark matter part, and here is an important parameter in our investigation named dark matter fraction, which is defined by the mass of the dark matter part divided to the total mass of the object. And pay attention that for both cases, the visible radius of the object will be the RB, which is related to the baryonic matter part. So here I can show you just an example for a dark matter admixed neutron star structure by considering PBC and PDC, which corresponds to the fractions here, 10%, 20%, and 30%. And for the DM core cases, which is related to more heavier bosons, like, for example, 400 mega electron volt and lambda, which is the coupling equal to pi, we have a DM core structure. Here, the dark matter part is shown by solid lines, and the baryonic matter part with dashed lines. And again, here we have for DM halo structure, which is related to lighter bosons, for example, 100 mega electron volt, lambda equal to pi, we have a DM halo structure. And you can obviously see, for example, the DM core radius is about 5 kilometers, but we have a BM shell around it. But in this case, the BM radius is about 10 kilometers. However, we have a very large radius for the DM halo, about 30 kilometers, about 50 kilometers or 80 kilometers, which by increasing fraction, the radius of the DM part will increase. And in this case, we will see a decrease in the BM radius by increasing the fraction. And now I show you the mass radius profile of this object, which is a very important observable quantity, because we have a maximum mass limit for the neutron star, for example, from the latest NICER results, which is around 2 solar mass, and we can constrain our dark matter model by this observable results. Here I show you the mass radius profile. This is for the DM core, and this is for the DM halo, again for 400 mega electron volt lambda pi and 100 mega electron volt lambda equal to pi. You can see that when we have a DM core, we see a decrease in the maximum mass and radius, and pay attention that this black solid line is related to only baryonic matter without dark matter to see the difference better. And here we can see that we see an increase in fact maximum mass and radius, which with these effects we can compare and constrain the effect of different dark matter bosons, in fact different bosons masses and different couplings and also fractions. You can see also the effect of fractions, that for example the more fractions that we have here, the decrease is more, and here also the increase is more. So, and the other observable quantity that I want to talk about is the tidal deformability, which is related to the deformation of the neutron star in binary systems, because of tidal forms, the neutron star in binary system deforms, that we have induced quadrupole moment, and we have a tidal deformability, which is and the external tidal field in this situation, and the lambda t is, which is the tidal deformability, has relation to the radius to the Phipps power, and this Kdo is the dimensionless tidal log number. and r is the radius of the star. And here you can see that K2 will be calculated by Tov equation. So it is related to the neutron star matter and the EOS. So this is the point that you can see that how by considering the tidal deformability, we can impose constraint on the, for example, neutron star models, or in our case, the dark matter model. And then we define a dimensionless tidal deformability, which is the capital lambda, and has relation also to radius and mass of the object and K2, and from this event GW70870, we have upper limit for tidal deformability, which is in this case dimensionless tidal deformability less than 580 for mass equal to 1.4 solar mass. And here you can see a graph related to the tidal deformability in terms of total mass for different boson masses and fixed coupling and fixed fraction. Pay attention that the gray solid line here is related to the 1.4 solar mass, and the gray dash line is the upper limit for tidal deformability. And here we can see when we consider different, in fact, boson masses, by increasing the boson mass, we see a decrease in the tidal deformability, which is related to the DM halo to DM core transform. Because as I said, for lighter bosons, we have DM halo, and for higher massive bosons, we have DM core. And you can pay attention to the cross section and to the cross points, or we can say the intersections in between these graphs, and also the solid gray lines, that we can see that which one is consistent with in fact the observational limit. And here we can see better that tidal deformability crucially depends on radius. And here again, it is the tidal deformability in terms of radius for exactly the case that I showed before for different boson masses and lambda pi and fraction equal to 10%. And colored vertical dashed lines are related to the radius of the mass equal to 1.4. And you can see obviously that we have a DM core to DM halo transform and the increase in tidal deformability. As you can see here, I should say that the black solid line here is related to the only baryonic matter, and you can see that the DM core structures, the pattern of the radius is very similar to the only baryonic matter, because the radius of the object is calculated based on the equation of a state of baryonic matter. However, for the cases that we have halo, the pattern of the radius is not similar to only baryonic matter curve, and we see an increase in the tidal deformability, obviously. And again, you can see the cross sections between the curves and the dashed lines here. So here also is the effect of changing the dark matter fraction for a fixed mass, boson mass, and a fixed cooling. And again, we can see that when we have DM halo, which is related to the higher fractions, we have an increase in the tidal deformability. And for the lower fractions, which in this case we have a DM core, we see we have a low value of tidal deformability. And pay attention, for this case of mass, which is a moderate mass in our investigation, we will see a DM core, DM halo transform by increasing the fraction. And here you can see again this DM halo DM core formation by changing dark matter fraction for this mass equal to 200 mega electron lambda pi, which we can see obviously here. And we see that again with the increasing the fraction, the DM halo increase tidal deformability. However, the DM core decrease the tidal deformability, which we can obviously see here. And here is the transform that happened by increasing the fraction. That, for example, in these cases, that is, we have the DM core, we see some similarity to the only baryonic matter, which is the black solid line. And then when we have a DM core, we see increase in DM halo, we see increase in tidal deformability, and we see a change of the pattern of the tidal deformability in terms of radius of the object. And I should emphasize that in all our plots, the radius of the object is the outermost radius. In fact, for the DM halo case is the RD, which is the dark matter halo radius. And in the case for DM core, it is RB, which is related to the BM radius. And as a conclusion and summary, I should say that we consider a self-interacting complex scalar field as the dark matter candidate in a dark matter admixed neutron star, and we check and investigate the DM core and DM halo formation by considering different coupling, boson mass, and fractions. And as I said, we have two important observable quantity: the mass radius profile and the tidal deformability, which we show that for DM core we see a decrease in mass, in radius, and in tidal deformability, and for the DM halo we see an increase in all of them. And by considering these two important observational results, two solar mass as the maximum mass of a neutron star, and the upper limit that we have for tidal deformability related to GW170817 for mass equal to 1.4, we can constrain our the parameter space of our dark matter model, which you can find, I think, by the next year or by the next week or by the end of July in our paper, which will be appeared on arXiv. Very interesting results and plots related to the constraining the parameter space of dark matter model by combining these two observational results. And as an outlook, I want to say that we are in a golden age of neutron star investigation because of different telescopes, for example, NICER, LIGO, Virgo, CAGRA, and the new generation of the GW detectors, Einstein telescopes, and the X-ray telescopes, radio telescopes, which we can investigate the structure of neutron star, or maybe as a result shed light on the nature of dark matter or the model of dark matter. And especially in our investigation, radius is an important constraint, which we already have some results. And by combining, for example, mass of the different measurements of mass, tidal deformability, and radius, we can have a very strict constraint on the parameter space of dark matter model. And also the strange objects that we can see in these by these telescopes, for example, the GW190813, which people believe that it is the lightest black hole or the heaviest neutron star, which we can in fact have some answer for this strange object by DM halo formation. And I should emphasize that for some special, in fact, cases that the dark matter, that the mass will be observed based on the GR, and the radius of that object will be, for example, measured by the optical techniques. If we see some inconsistency between the result, it is a very, very important sign for our model, because as I said, for the DM halo, the total mass is not inside the total radius of the object. So this inconsistency will be very important for our investigation. And as the last point, I want to show you here is the picture of Jahan Square in Isfahan in Iran, which I hope that after this strange situation that we have in the world, this COVID-19, we can have you as a meeting in ICRANet Center of Isfahan. However, we will have a meeting on November, a virtual meeting. We will have some interesting talks from ancient Persian astronomy to the new developments. And thanks a lot for your attention.
Thanks a lot for this really interesting talk, and really waiting to look at your paper, because I think is providing really interesting limits on dark matter. And also I appreciated the photo of Isfahan that looks really marvelous. So I hope it will be possible maybe to have a meeting in real life in Isfahan, because it looks so beautiful. So,
thank you very much.
Questions. I have myself a little question. I am speculating recently, not only me, but me too, about the possibility that dark matter is made actually of nuggets of strange warm matter. I suspect that in that case, we would not get, so to say, any extra constraint, because if dark matter is really made of the same matter, in a sense, that compass stars are made of, then the limits that we observe on compass stars in normal ways would be essentially identical to the limits that we need to impose on dark matter. I imagine that the answer is yes, but maybe you can tell if in my reasoning there is some mistake.
I think because we have some, as I understand exactly your question, because we can have, let me share my screen again. We have different scenarios, as I said, for production of dark matter in neutron stars. And based on the scenario that you are talking about, I think we maybe we can talk about some single fluid dark matter neutron star. Maybe if we want to check these based on the argument that you are talking about. It is my point of it, but I'm not exactly sure about this comment.
Thanks. Onas, please.
Yes, I have two questions. I will start with the one that probably is more interesting to me. It's related to this. Is there a way to falsify this constraint or this model in other contexts where dark matter is also important? For example, the rotation curves of galaxies?
We have some, we can say we have some constraint because, for example, the range of the coupling that we are using, we can have some relation for it that can be derived. Can you see my screen?
Yes.
Sorry, let me show you to better the answer. Here is, you can see the range that we consider for the coupling, which can be derived based on the cross section that can be derived by observational limits from the cluster and galaxy cluster and the galaxies and the clusters. So in this way, by having this limit for the coupling constant, I think we can probe this, in fact, the context based on the points that you are talking about.
Okay.
This is yeah.
Okay.
Here you can see that we have a range for coupling that is derived based on considering the sigma over m, which is coming from the cluster and galaxy and clusters, which is around 0.1 to 1 that you can see here.
Okay, and the second question is, how does the stability of the star change with the two equations of state?
The stability of a star is related to two different things. One of the things that we should pay attention is that if that we consider only the boson star matter, in fact, the dark matter, without considering the stability of the whole object. For example, if we want to consider the stability of whole object, exactly what we have for neutron star, we can see that after the maximum mass, we will have a decrease, which shows the instabilities, and also we can check with radial oscillations and so on. And the other cases is that when we have that we consider the instability based on the bosonic dark matter, which for example we can have Bose-Einstein condensation, and maybe we can have a black hole inside the neutron star, which this is a problem in our calculation. However, because we are working in a strong coupling regime and we consider self-interaction, mostly people believe that we can neglect this problem, in fact, the black hole formation regarding to the only dark matter equation of a state, and we can probe this instabilities based on the general instabilities for dark matter admixed neutron star that you can see, for example, here in these MR relations.
Okay, thank you.
You're welcome.
Okay, I think that we came at the end of the session, and Jorge, you close the session. And personally, I thank really all the speakers. It was a pleasure to meet all friends. And I have to leave because somebody is calling me. So I apologize. And thanks a lot. Thanks a lot. Thanks a lot.
So thank you to thank you to Alessandro. Also, I would like to thank all the speakers of the session of today, not only the speakers of today, but also the speakers of yesterday. So as you know, we have two sessions, both of them very interesting from the first to the last talk. So yes, thank you for everything. So we expand a lot of topics related with neutron stars, so aside from elasticity of the crust, the cooling, pulsars, different kinds of interior structure. Now with the last talk, even the possibility of having dark matter inside neutron star with touch on gravitational waves, on neutron star, on binary mergers, accreting neutron stars. So there are really a lot of topics. And so I'm waiting and look very much forward for your contributions for the proceedings of this splendid session. And thank you again for everything. And I hope to meeting you in the near future personally. I mean, physically.
Me too, I resurrected. So I resurrected, and I extend what Jorge is wishing to all of you.
And I should say again that we have in November in a meeting in this ICRANet Center of Isfahan, and I kindly invite you for that meeting. It's a virtual meeting.
Thank you. Thank you, Dawood. So so you are free now.
Thanks a lot.
Matthias,
bye
Matthias, long time.
Okay, so
see you. I really want to come again to Frankfurt.
Oh yes, please.
And you were supposed to come to Ferrara, you recall, a few years ago. So let me invite you again to Ferrara. Please come.
Okay, so probably not this year, but next year for sure.
Okay, I take your word. Dani, also it was a long time that we don't meet. Very nice to meet with you again.
Yeah, Alejandro, a long time. Yeah, hope we meet directly soon. Okay.
So good.
Okay.
So thanks again.
We just
goodbye
leave.
to everybody.
You will just leave. The session will close automatically. Okay.
It's automatic.
All right,
collapse. The world is collapsing in 5 minutes. The end of the world is coming in 5 minutes.
Thank you all. Bye.
Thank you everyone. Thank you. Bye.
Ciao.
Bye Mattias. Bye everyone.
Ciao Olga. Ciao.
Ciao Alessandro, grazie di tutto. Ciao.